Tu es trop grand pour comprendre des choses aussi petites.
Vous allez lui faire un enfant.
Les papillons.
Tu es trop grand pour comprendre des choses aussi petites.
Hello, good morning to all of you. I welcome you all to this session, first session of this third day of the conference. I welcome Professor Eckert and Professor Rishi Raj. So I request Professor Rishi Raj to start the session. Thank you.
Good morning, everyone, and good evening to Professor Eckert. Okay, it is my pleasure to chair this session by Professor Eckert, keynote number 9. The title of the talk is Optimal Control of Water Turbulence for Dissimilar Heat and Momentum Transport. And I'll read out the brief bio of Professor Eckert.
No, that's not the topic of my topic. Mine is
That's what the abstract booklet says. Okay.
No, it's not. So I don't do optimal control. No, I do heat transfer studies.
Yeah, that's why. Okay. Sorry. Okay. I'm sorry for my mistake, and we'll know more about the title. But I'll talk about Professor Eckhart's bio. Professor Eckert is the head of the department and R.J. Reynolds Professor in Mechanical Engineering, Mechanical Aerospace Engineering Department at NC State University since December 2017. He previously served as the Associate Vice President for Research Programs at Virginia Tech. He also held the title of Rolls-Royce Commonwealth Professor for Aerospace Propulsion Systems at Virginia Tech. He was also the founder and director of Rolls-Royce University Technology Center for Advanced System Diagnostics at Virginia Tech. It is one of the 30 centers around the world prior to joining the NC State. He was in the Mechanical Engineering Department at Virginia Tech from August 2007 to September 2017. After 9 years at Louisiana State University and 2 years at Rolls-Royce Aviation Engine Company in Indianapolis. He received his PhD from Texas A&M University and MS from Arizona State University. He has over 25 years of experience in heat transfer related research. He has published over 250 journal and conference articles, 3 patents, and co-authored a book and 3 book chapters. He currently has funding from Solar Turbines, Trilotus Aerospace Systems. He has been working on gas turbine cooling and heat transfer issues since 1989, including a stint as a design engineer at Rolls-Royce Indianapolis before his academic career. Dr. Eckert has also served as a summer faculty fellow at AFRL in 2003. He is well known for his contributions to heat transfer experimental methods. In 2004, he received the inaugural ASME Burgels Rosenhau Young Investigator Award in Heat Transfer for significant contributions to the field of heat transfer by a researcher under the age of 36. He is also editor-in-chief for the ASME Journal of Thermal Science and Engineering Applications. Personally, I have known him for a while now, almost 14 years since his days at LSU and then Virginia Tech. And I wholeheartedly welcome him to this talk, and we look for the high energy and enthusiasm that we know of him. And we would have the talk first, followed by some question and answers. So over to you, Professor Eckert.
Thank you, Richie. Let me see if I can share my screen in a minute. Can everybody see it now? Can we see the talk?
Yes, we can.
Okay. All right. So my topic is not what Rishi was talking about. Actually, I had sent my abstract on heat transfer studies for gas turbine hot gas path components. I know that this is the fluid mechanics conference, but there's a lot of fluid mechanics in what we do in heat transfer and gas turbines. So there will be a lot of connection that I can share around with you. But I want to thank you, Professor Dalal, for inviting me for this. And I was really looking forward to being in India at this time and being in Guwahati after almost 15 years. It would have been nice to see the development of the campus compared to what it was. I guess we are in this new era where I don't get to be where I want to be, and none of us can be. So hopefully it'll all end in another 6 months, and we can all see each other in reality in fair place. So just quick background, gas turbines are well known. Everybody knows what gas turbines do. Gas turbines are very simple. If you look at it, it is just putting a compressor, a combustor, and a turbine together. It's very simple, but on the other hand, it's very difficult to actually implement. And gas turbine high temperatures are getting upwards of almost 1800 C right now. So higher the turbine inlet temperature, higher is the efficiency. And also, as we go to higher temperatures, the possibility of creating NOx increases. So essentially, we are trying to figure out how to operate these gas turbines with very lean, low pollutant conditions, especially NOx, and also to a large extent unburned hydrocarbon fuels. But more importantly, there is also the other issue of how long can we operate apart under these extreme conditions, very high temperatures and high pressures. Upwards of 20 bar and 1800 C puts significant pressure on everything that looks red here. The temperatures, so you need long operating conditions. How are we going to ensure that these things will survive through the loads that we put it in, through the fuel composition that we put it in? So it's a very complex machine, but it runs on a very simple concept. If you look at the combustor itself, it's primarily where the air from the compressor comes in, which is by itself is about 550, 600 degrees C, which enters the combustor, and then you add the fuel in, and then the fuel burns and then creates the temperatures of upwards of 1800 C right at the entrance of the turbine, and then you're going out exhaust. And for an aero engine, you use this for exhaust propulsion. For gas, for a power generation, you would actually put a power turbine downstream of it and extract the power out of it. And energy is released primarily because of the fuel burning in there. And the crucial role of combustor in determining engine's operating characteristics is primarily fuel efficiency, levels of emission, and the stability and response of the flame. That means you cannot operate, the flame regime is limited. You cannot operate it too rich or too lean. So you have to come up with the optimum conditions. So modern gas turbines are operating upwards of 2000 Kelvin, and the high pressures of 40 bar. So it's going to keep pushing. We'll keep pushing. And the combustor itself looks very interesting like this. It's got a lot of sleeves where the cooler air keeps coming in and mixing with the primary zone combustion. And actually you get dilution holes that are adding more and more cooling air. So slowly, so get the temperature down here to under 2000 Kelvin. But if you think about it, the temperature right here in the middle of the primary holes where the fuel is mixing and rich, you can upwards of 32, 3300 Kelvin. So you cannot have 32, 3300 Kelvin coming and touch with the surface. So that's why we put in a lot of cooling air. But if you burn it lean, you can burn it about with the primary zone at 2400, 23, 2400 Kelvin, but you still get the temperature of 2000 Kelvin at the exit. Then you have to redesign this combustor into different. So I'll talk about that in a little bit. Downstream of the combustor is the high temperature gas turbine blades, the blades and the vanes. And you can see that just outside the combustor, 1700 C, which is about 2000 Kelvin, you can see the first stage vane here, and then the first stage rotor here. Both of them have to be extremely cooled to even survive even few hundred hours. So we are pushing a lot of coolant that is coming from underneath the combustor, bypassing the combustor, and that's about 10 to 15% of the total air. And that air is going through the blades. As you can see, it's got complex internal passages, and then complex internal passages have cooling air coming out of it, and then the cooling air then protects the blade and ensures that the blade survives at least the minimal amount of time that we design it for. So complex things happening. We got hot gases, high turbulence, complex internal turbulated channels, and a lot of fluid mechanics happening in this geometries. So first I'll talk about the challenges of turbine airfoil cooling, and then I'll go into combustors. Turbine airfoil cooling, again, started in typically the work started in 1970s when the turbine external temperature went over 1200 C, and then we stopped using stainless steel mixed materials, and then we moved into titanium and nickel alloys. So if you look at it, the blade actually has a lot of internal features. The flow comes in, goes through complex passages, 180-degree turns. It has rib turbulators to enhance heat transfer, so you can constantly break the boundary layer and produce new fresh fluid coming back to the wall and increasing heat transfer. You also have impingement cooling, where you have jets impinging on the insides of the blades, and then you also have pin fins at the back end to help you turbulate the flow. In addition to that, some of the air is injected through holes on the outside of the blade, which is called film holes. And these film holes are also complex designs. They're not as simple as they look. They're not circular holes. They're shaped into different directions to produce maximum cooling. So all this is happening on the blade. And in addition to that, the outside of the blade is facing the airfoil surface curvature. There is boundary layer transitional behavior. You got free stream turbulence coming out of the combustor. Then you got the airfoil surface roughness, because you coat these blades with what is called the thermal barrier coating. And that thermal barrier coating has some surface roughness to it, which enhances heat transfer. And then again, you got the location of these holes which are also very complex. Then, of course, you got the flow separation and reattachment, especially on the suction side, trailing edge. And then you have the exit Mach number effects. You have shocks, potentially, if you have transonic conditions. And then, of course, in fluid mechanics, the basic Reynolds number effect. So if you think about it, the turbine inlet temperature is about 1700 C. The blade material melting point is 1000 C. The coolant air temperature is 700 C. To make this arrangement possible, you have to design efficient cooling concepts with only 15% of the air. So that means the outside air is 85%. You've got 15% of air going through this blade, which are going to produce the temperature that you want, which is below 1000 degrees centigrade. So a lot of interesting things happening here. If you want to simply draw this into a flow chart, turbine cooling temperatures are primarily focused on high pressure turbine airfoils, and you need internal convective cooling. Then you got the film cooling, and of course you want the material. You want the material to be high temperature, high strength nickel or cobalt based superalloys coated with TBCs. Then you put all this together, and then you design what is called the thermal mechanical design to come up with acceptable levels of thermal stresses and aeromechanical response. In addition to this, you can also pre-treat your cooling fluid. There are people who have tried using water mist. People who have used fuel cooling, all kinds of stuff where you can pre-treat a coolant and push it through the airfoil, and that has its own challenges. And that's the reason why it's not implemented so many times. I won't talk too much about that. If you look at a basic heat transfer situation, if you have the outside air, which is the gas air, which is has a temperature, and then there is the TBC coating, which has a thermal contact resistance here, and then you have the metal resistance, and then you got the interface, and then the metal resistance, and then you got the internal cooling heat transfer. So the goal is to enhance this heat transfer and decrease this heat transfer. So with the two things that are happening, one side you're trying to reduce the heat transfer, one side you're trying to increase the heat transfer, so that ultimately this whole metal and the TBC temperature would come under 1000 degrees C, so it won't melt. So the enhancement of the heat transfer here is very, very important. So you have to increase the heat transfer to 3 or 4 times what it would be normally by adding ribs and pin fins and impingement and all those other things. And also at the same time, you have only a limited amount of air that's available to you at a limited pressure. That means you can only push so much amount of cooling air through the blade, given that the pressure ratio is limited by what the compressor is putting out. So you got to make sure that your enhancement in heat transfer is unaffected by the increase in pressure drop that you get by adding extra features. And that ratio is called the thermal hydraulic performance. And if this eta is greater than 1, then you are getting benefit of putting complex features on your airfoil. So you got to first calculate the heat transfer enhancement you're getting over a smooth surface, and then you also need to calculate the amount of pressure ratio you're getting because of the surfaces, and then you calculate this ratio, and this ratio has to be greater than 1. So if you look at cooling designs by itself, heat transfer augmentation goes up to 6 times what a smooth surface would be, but friction augmentation also can go up. But if you look at what is the impingement cooling is right here, where you can get around 3 to 3.5, but the pressure ratio is also not very high, so 3.5. So you would automatically get about 1.2, 1.3 in the thermohydraulic performance. But if you want very, very high heat transfer up to 5, you have to go to turbulated channels or rotating impingement and this kind of conditions, but you also increase your pressure drop. So the goal is to design a cooling system which will push you towards this range on the other side of Reynolds analogy. And how do you do that is where the challenges are. That means you want very, very high heat transfer, but very low pressure drop increases. So looking at impingement, you can get rib turbulators with V-shaped ribs, which are complex ribs, or you can create impingement by going through holes between channels, but causing swirl-induced turbulence, or you can go with crisscross ribs like this to enhance heat transfer by adding more contact surfaces in the heat transfer situation. Or you can go with twisted tapes, or you can go with pin fins, which are complex geometries, and you can look at impingement on pin fins, which can increase heat transfer further. And there is some more concepts like tangential injection, which is also very complicated, again, very difficult to implement in a gas turbine situation. Again, so goal is to move the research trust towards the other side of Reynolds analogy. So we took all the data out there on all kinds of geometries and put it together. And you can see that the one geometry, which is dimples, which is concavities on surface, which enhances because of a different kind of turbulence. It's called turbulence bursts, and enhances heat transfer, but does not cause a huge pressure drop. So you get a heat transfer ratios of about 2.5 with only a pressure ratio increase of about 4. Whereas if you go to ribs and complex ribs, you are getting pressure ratios of 15, but your heat transfer is about 4. So you are giving up a lot to get a lot, right? So this is where the technology has been going, which is not the favorable direction. Ultimately, we want to get to 5 or 6 in heat transfer enhancement, but the problem is the direction we are going, our pressure drop is also going up to 15 to 20 times the smooth surface. So where are we headed? As one option is to see if we take ribs and dimples and combine and see if we can come somewhere here. That's one of the goals, right? So why didn't we do that before? Before we could not do that because we could not manufacture them. Most of these designs were unmanufacturable. So most of the designs that our researchers present in papers are never been manufactured in an actual gas turbine. Even the work that's done in the 80s and 90s have not been still used in gas turbine blades. So how are we going to ensure that? Of course, the game changer is additive manufacturing. Okay, the market never demanded before, but now that additive manufacturing has come in, we can create these geometries much more easily because we can print them rather than do casting or machining, which is all more demanding in terms of, and also it's also impossible to make some of the geometries, especially the crisscross ribs, that you cannot make those. So the direct metal laser sintering is what we are trying to do, where we are trying to use a laser guided addition of fine layers of metal powder. Basically, we get the metal powder, the actual alloy is in metal powder, and then you fuse it with a laser guided, and the laser guides the fusion in such a way that it creates the blade, and with all the complex features in it. So there's a lot of work going on in this, especially by the manufacturing companies and also by all the gas turbine companies like Pratt & Whitney and Rolls-Royce and GE. So there's a lot of effort going on in this. Pratt & Whitney has been doing this in 1980s, if you won't believe it. And some of their parts are already there in Pratt & Whitney 1500 GE engine. They have actually started making their own parts, and they're all based off of nickel superalloys. And interestingly, they have a couple of parts have already been tested in actual engines. GE Aviation plans to manufacture 100,000 parts. They already made it in their 9X engines, and $6 billion a year. So a lot of interesting things going on, some research projects that have been made. The important takeaway is we can do all this now with all this. Geometries can be printed. So just to give you an idea here, this is a smooth channel where the flow comes in and goes through 180 degrees. This is experimental data. And this is the rib channels with 60-degree rib, which is already there in the engine. And you can see the heat transfer enhances the direction of the ribs with a very high heat transfer here, and it's low heat transfer at this end. And again, you get a new boundary layer forming in this direction, and then you got flow turning, and you got higher heat transfer. If you put a V rib, you see a much more higher heat transfer with the V rib. Again, V ribs are not used in engines. W ribs gives a little bit different geometries, and here some CFD shows how the vortices are generated in each of those geometries. And you can see there is not really any vortices, but only a secondary flow generated in the 60-degree ribs. At the V ribs, you see this fusion of vortices, small vortices in the center, whereas W ribs shows this 4 little vortices on both sides. So if you see all this, basically what is happening is an increase in turbulence transport, and that's basically what is causing the higher heat transfer in all these geometries. If you look at dimples, as I told you, dimples are very complex. They are basically cavities, and if the flow goes in and it reattaches and down inside the dimple, and then there's a turbulence burst forms that blows the flow out of the cavity, and it comes out and reattaches downstream and causes a higher heat transfer. And there are a lot of good papers out there on dimples and dimple mechanisms. Again, there's a limitation on how much heat transfer you can get with dimples, but it's an interesting phenomena. Now, if I take the ribs and I put the dimples in between the ribs, which I can do with additive manufacturing. What is the concept? How is that going to help us? So what we did is we took 60-degree ribs and added dimples, V ribs added dimples, and then we added W ribs and added dimples, and see what happens to the heat transfer. So if you look at it first, let's look at 60-degree ribs. You know that the heat transfer enhances. And then with only dimples, the heat transfer enhances. But then you add both of them, you get almost significantly larger heat transfer than both this. What is happening is when the flow is actually inside the passage with the ribs, the secondary flows is creating even more smaller secondary flows around the dimples and adding extra turbulence that's generated locally in that region and enhancing the heat transfer further. Rather than here, it's just flat surfaces where there's no further enhancement. And you see that effect in V ribs, you see the effect in W ribs. You constantly are seeing this very complicated structure that are enhancing the heat transfer. And those fluid mechanics structures are the ones that bringing in the flow much closer to the wall and keeping cooler air close to the wall and just enhancing the heat transfer. So by adding this complex geometries, you are actually going to enhance heat transfer even more than it was before. So what happened was dimples are here, the ribs are here, the compound geometry produces a much higher heat transfer, and it's also going towards almost 4 to 4.5 enhancement, but only the enhancement is the pressure drop is only slightly more than what it would be with ribs. So what you're actually seeing is by adding a compound geometry, you can actually enhance heat transfer further. The only reason we didn't do before was we didn't know how to manufacture these things. But now with additive manufacturing, we can manufacture this. So there's a lot of research going on in focusing on how to manipulate the flow using complex geometries and enhancing the heat transfer further. So just give you an idea, how do we do experiment? This is the experiment of a rotating rig where we actually measure the heat transfer. You can see a V-shaped channel here. What you're going to see as soon as I click is you're going to see the channel is rotating at about 700 RPM. And these 3 cameras that are on the arm with the channel are going to rotate, and you will see the color changes, and that's what we capture to get the liquid crystal color changes, from which we measure the wall temperature, and from the wall temperature we calculate the heat transfer coefficient. So just see you here, the picture, the video here. As you can see, it starts rotating. And you can see the colors changing from blue to green, eventually to red, and then it becomes colorless. And we can capture all this with GoPro cameras, and then the cameras are then downloaded the images, and then we calculate the heat transfer. So this is a sample of an experiment we do in our lab. That's how those color plots were generated in the previous slides, the heat transfer. So we also do complex geometries like this, where instead of having traditional channels where the flow goes from here to here, we break it up into 4 different channels to enhance heat transfer. And then we also see all the fluid mechanics again in terms of what's happening. This is actually a blade that's rotating in this direction. So you got suction surface and the pressure surface. So we want to enhance the heat transfer on this surface and on this surface. We really don't care about what's happening on the inside. So we can actually look at the flow structure that are formed. One is primarily because of the ribs, and secondary flow generated because of the centrifugal buoyancy. Then of course the Coriolis force that's also acting on it, and all 3 forces that are acting on it will create a complex structure that enhance heat transfer on the surface. So you can see that these are what's happening in terms of local 4 little cells are formed. And then the pseudo trailing wall and the pseudo leading wall are not really active, and only the leading wall and the trailing wall are active in the heat transfer. So if you take these geometries and you calculate the heat transfer again, you can see that with and without rotation, there is no effect of rotation on these geometries. So what we are trying to do here is, what happens if you rotate the surface? You want to have higher heat transfer or lower heat transfer, but we want it to be unaffected by rotation. So rotation should not change the heat transfer. So as you can see, there's not much effect of heat transfer with rotation, and that's one of the things that you can generate with new geometries. A little bit of more detail here. without the regular channels would be, you see much higher heat transfer on one side, very low heat transfer on the other side. But if you see the new geometries, they are much more flatter and much more. In fact, you can get a heat transfer enhancement of up to 5 or 6 without increasing pressure drop. So what we are trying to do is change the convention on how designs can be made and also fabricated, and these companies can then make this in actual blades and actually put them in real engines without worrying about durability and life. So a little bit more data on this, how much enhancement you can get, up to 4.5 with the geometry compared to traditional geometries of about only 2.5 to 2.7. So that's basically what the goal is to increase the heat transfer. So our group is currently working on optimization of novel cooling design, working towards AM fabrication, and eventually looking at porous structures and things like that, very complicated geometries that can now be made with additive manufacturing. So now I'm going to skip to combustor work that we have been doing. As I told you, I'd show you what a combustor is. This is the old combustor and this is the new combustor. Old combustor did not have pre-mixed fuel, the air fuel mixed right before they exited. And now we mix the fuel and the air before, and we push it through, and then we burn it at a much leaner condition. So we get about 2900 Fahrenheit compared to 3600 Fahrenheit, but overall temperature is still the same. So why do we do that? Because we're reducing NOx. The idea is to reduce NOx, and you can do a lot of that but just by reducing the core temperature from 3600 to 2900 F. So the way we do it is we have swirler fuel nozzle, the air and the fuel enter this when they get out, and then the swirling flow mixes the air and fuel, and then you light it up, and then the flow comes in and impinges on the surface, and some of it recirculates, and then you have these 2 corner recirculations, and then this is how the fuel nozzle looks like. The pilot fuel that the air fuel comes out, and then the main fuel, you first light the pilot fuel, and then the main fuel enters, and then they mix, and then the pilot fuel causes the main fuel to light up, and then you get the flame. And I'll show you quickly a little bit about it. So why does swirl help? Swirl helps in increasing the mixing and just enhances a much better flame stability. So there's a lot of work going on with how swirl flows help in improving stability of flows. Even though it causes higher turbulence, actually enhances the flame stability. We built a combustor rig to actually do this. So you can see the combustor rig, the flow comes in. This is our combustor right here. And you can see the schematic here. We have optical access for flame diagnostics, and we also can measure heat transfer both with IR thermography and thermocouples, but we also do PIV on it, and I'll show you some PIV results. We preheat the air just like in a compressor, and we can preheat it with a 200 kilowatt heater. We push in about 2.8 pound mass per second, which is about 1.3 or 1.2 kilograms per second at 120 psi. So the flow comes in, and this is how our combustor looks like. This is our fuel nozzle. It's an actual fuel nozzle from a solar turbine's combustor. And then we push in our fuel air ratio, and then we light the fuel up, and then we can get a very interesting flame. So what we do is we have a light source, which is a laser, and then we have a photon camera that takes images at high speeds, and then we use alumina CD particle to disturb the laser sheet, basically in terms of getting the reflection out of it. And then of course the external trigger is set up so that we get the trigger to get the 2 images out, so we can calculate the velocities from the 2 images that we get. So if you want to look at it, this is how the flame looks like. As you can see, right side of the image is going on. Both the flames are going. You can see one with 0% pilot and one is a 6% pilot. And then we turn on the laser and actually capture 2 images, and then we do cross correlation and then calculate the velocities and the flame structures and the turbulence intensity and all this other stuff. So this is actually 1 atmosphere. It is not at high pressure. It is very low pressure. That the adiabatic flame temperature is at about 1800 Kelvin in this experiment. So if you look at it, this is how the flame looks like, and then you'll see the laser flashing in a minute. This is the full flame now, and then you see the laser flashing, and then you get the data from the cameras. We take the images, and then we cross correlate and then calculate the velocities from the PIV. So if you look at non-reacting, you see actually what is most interesting there. Non-reacting looks very haphazard. In fact, it has no structure, no coherence in turbulence. But when you start reacting, actually you see a much better organized flow, and that's the energization of the flow, right, where the flow is coming out of the nozzle and actually goes and impinges on the wall on the outside. So what you're actually seeing is the structure is better with reacting than with non-reacting. So if you make any heat transfer measurements with non-reacting flow dynamics, you are going to be completely off in what's happening at the near wall of the combustor. So essentially, this was one of the biggest findings about 3 or 4 years back. It shows that clearly that the non-reacting flow is not at all similar to the reacting flow in a combustor, and that's going to change everything there. So what happens inside, if you go and do the PIV measurement and actually look at the flow structures, you see a shear layer between the main flow that's coming out and then the flow that's coming back towards the swirler. And then there's the zero velocity zone here, and the zero velocity zone here, and the zero velocity zone here, and this is the pilot. Very, very complicated geometries. What's happening, and this basically causes a much more strong impingement here, which causes a very high heat transfer right here on the wall of the combustor, causing a very significant heat load, and that area is where most of the failure in a combustor occurs. And this was one of the biggest findings that we showed our sponsor. And so we need to put in more cooling air coming out at this location. Causing a very significant heat load, and that area is where most of the failure in a combustor occurs. And this was one of the biggest findings that we showed our sponsor. And so we need to put in more cooling air coming out at this location.
Good morning, everyone. Welcome to the day 3 of the FMFP 2020. I request Professor Himanshu Tyagi from IT Ropar to chair this session.
Hello, am I audible?
Yes, sir, you are audible.
Okay. So I welcome all the participants. I just want to double check that all the participants are already here. Okay. So let us go ahead with the first presentation of this particular session. And what is the name of the person who will be presenting it? I think the first talk is paper number 179, experimental study of internally cooled liquid desiccant dehumidifier assisted by solar regenerated. Yes, please go ahead.
Everyone, I'm Kalpana, research scholar from Department of Mechanical and Industrial Engineering, IIT Roorkee, presenting our paper Experimental Study of Internally Cooled Liquid Desiccant Dehumidifier Assisted by Solar Regeneration. These are the contents of my presentation: introduction, principle of desiccant cooling, literature reviews, objectives, methodology, experimental setup, data reduction, results, conclusions, and references. Introduction. With the fast development of economy and society, our modern life and industry consume large amount of energy for cooling. The increasing demand for air conditioning, particularly in hot and humid climates, has caused a significant increase in energy demand. This increase in energy demand is depleting the conventional energy sources, that is fossil fuels, natural gas and coal. Burning of these fuels is also responsible for CO2 emission. The increased emission of CO2 and other greenhouse gases will cause many climatic disturbances because of increase in global temperature. Renewable energy, which was not utilized so well in the earlier, is attaining attention now because of cost and expensive commercial acceptance, maintenance is and its eco-friendliness. The conventional air conditioning system is better for all the required indoor conditions. It controls both the temperature and humidity, but it has some disadvantages, like it consumes more electricity and not good for the environment because it depletes the ozone layer and causes global warming. One more problem with the conventional air conditioning system is that during the humidification process, air needs to be cooled below the dew point temperature, and after that it is reheated up to the required indoor condition. As a result, significant amount of energy is lost in overcooling and reheating. Overcooling is also responsible for the growth of molds and bacteria that affects the quality of the indoor air. The desiccant system is a worthy replacement of a conventional air conditioning system to tackle latent load. The major benefit of this system is that the cooling process requires no mechanical compressors and no CFC refrigerants. It can also diminish the electricity requirement by utilizing low-grade energy like industrial waste, solar energy, and geothermal energy. Principle of desiccant cooling. Desiccants are synthetic substances capable of absorbing water vapor due to difference of water vapor pressure between the surrounding air and desiccant surface. Figure 1 shows the schematic of liquid desiccant evaporative cooler. It consists mainly 3 components: dehumidifier, regenerator, and cooling unit that may be direct and indirect evaporative cooler. The task of the dehumidifier unit is to remove the moisture of the incoming process air by bringing into contact with desiccant. The regeneration unit is used to regenerate the diluted solution flowing from dehumidifier unit to an acceptable concentration so that the continuous operation of the cycle can be maintained. This is done by heating the desiccant material to its regeneration temperature. The role of cooling unit is that it handles only sensible load. Literature reviews. These are some selected papers which we have gone through for our work. Objectives. The present study has been carried out with the following objectives: modeling of an internally cooled liquid desiccant dehumidifier using outside evaporative cooler, use of market shaped channel solar collector for regeneration, parametric performance study for liquid desiccant air conditioning system, and the evaluation of effectiveness of the dehumidifier. Methodology. In order to attain the objectives, the following methodologies and material for the equipment for the experiments are used. First For the experiment, calcium chloride is used as a liquid desiccant. Prototyping of the dehumidifier and regenerator in the laboratory. Measuring temperatures of air, humidity of air, mass flow rate of air and solution, and concentration of solution in regenerator and dehumidifier using appropriate tools and equipments. Taking data using data acquisition system with proper instruments and analyzing the data for the experiments. Experimental setup. The main component of the setup is dehumidifier and regenerator. In our system, we made a dehumidifier and regenerator in a single unit as shown in figure 2. The middle portion is act as a dehumidifier and the bottommost tank is act as a regenerator. The dehumidifier is made up of 25 316 stainless steel tubes stacked with equally spaced 32 aluminum sheets as shown in figure 2. The tubes are arranged evenly in zigzag manner. All the tubes are connected with two tanks at the top and at the bottom. The top tank is used for solution distribution inside the tube, and the solution is flowing from the top to the bottom in the form of film inside the surface of the tube, whereas air is blown in the reverse direction from bottom to the top inside the tube. The dehumidification process is going on inside the tubes. After the dehumidification, the diluted solution is collected in the bottom tank. The bottom tank has two compartments. One is for the upper compartment is for the collection of diluted solution and the bottommost compartment is for the regenerator. The two compartments separated by a horizontal perforated perfect sheet with the holes of uniform diameter and uniform gaps between holes to deliver the diluted solution to the bottommost compartment. The bottom compartment has a copper coil of diameter of 10 mm at bottom, which acts as a heater for regeneration of diluted calcium chloride solution. Inside this coil, hot water is flowing, which is coming from the market-shaped solar flat plate collector. All the tanks are made up of 0.8 cm thickness perfect sheet, as it is non-corrosive to the solution. As you know, the dehumidification process is an exothermic process. So during dehumidification, inside the tube, solution temperature is increases. So to maintain the solution temperature inside the tube, fins are provided outside the tube. This is figure 3 shows the actual experimental setup. Figure 4 shows the schematic of the experimental setup. In this, a solar collector unit is provided the hot water in the regenerator for the regeneration of diluted solution, and the main test section consists of dehumidifier and regenerator as a single unit. The sprayer and constant temperature bath is used to provide the required temperature and humidity of the air at the inlet of the dehumidifier.
The blades are attached to
Data reduction. The collected data are used for calculations and analyzing results for the parameters considered during the experiments as given below. First one is absolute humidity reduction. It is the difference between the humidity ratio of inlet and outlet air of dehumidifier. Second one is dehumidifier effectiveness. It is the ratio of actual humidity ratio reduction to the maximum humidity ratio reduction. In this, equilibrium humidity ratio is calculated by using equation 3. In equation 3, the value of where PS is the solution partial vapor pressure and B is the atmospheric pressure. The value of this partial vapor pressure is calculated from the correlations introduced in equation 4, which is given by Gadet et al. The operating values of the constants used in equation 4 is provided in table 1. And the last one is enthalpy effectiveness. It is defined as the ratio of difference between the inlet and outlet air enthalpy of dehumidifier to the difference between the inlet air enthalpy and equilibrium enthalpy of air.
Thank you, Professor.
Results. Figure 5 shows that the increase in solution volume flow rate for the fixed inlet temperature and relative humidity increases the absolute humidity reduction due to increase in vapor pressure difference between the air and solution. Figure 6 shows the same variation of absolute humidity reduction with solution volume flow rate at different relative humidity ratio. From figure 5 and figure 6, it is concluded that as the relative humidity increases, the absolute humidity reduction is also increases. Figure 7 shows the variation of temperature of air with solution volume flow rate at the fixed value of relative humidity and fixed inlet dry bulb temperature. As the solution volume flow rate increases, the temperature is decreases. In this In the figure 7, red line shows the outlet temperature and the blue line shows the inlet temperature. From the figure 7, it is clear that the inlet temperature is lower than that of the outlet temperature for the same flow rate. This is because of the dehumidification process. As dehumidification is an exothermic reaction, so outlet temperature of the air is increases. Figure 8 shows the variation of absolute humidity reduction with inlet relative humidity at fixed inlet temperature and solution volume flow rate. Evaluation flow rate. With inlet relative humidity, the absolute humidity reduction is increases.
Yes, sir. This is Shantanu.
Figure 9 shows the variation of absolute humidity reduction with regeneration temperature at fixed flow rate and fixed inlet conditions, that is dry bulb temperature and relative humidity. As the regeneration temperature is increases, the absolute humidity reduction ratio is also increases. This is because the increase in regeneration temperature removes more moisture from the solution surface and hence the absolute humidity reduction becomes more effective. Figure 10 shows the variation of absolute humidity reduction and dehumidifier effectiveness with solution temperature. The red line shows the absolute humidity reduction and the black line shows the dehumidifier effectiveness. As the solution temperature increases, the dehumidifier effectiveness and the absolute humidity reduction both are decreases. Figure 11 shows the variation of dehumidifier effectiveness with relative humidity for the fixed volume flow rate and fixed inlet temperature of the air. As the relative humidity increases, the dehumidifier effectiveness decreases. The black line shows the results of our experiment, and the red line shows the results from the paper of Cheng et al. It is clear from the figure 11 that the present results for dehumidifier effectiveness are more than the Cheng et al. Paper in most of the cases. Conclusions. In the experiment, absolute humidity reduction increases with increase in solution volume flow rate for the fixed inlet air temperature and relative humidity. The increase in relative humidity from 68.4% to 92.8% for a fixed inlet air temperature increases the absolute humidity reduction from 5.56 gram per kg to 13.3 gram per kg for 20 liter per minute solution flow rate. The increasing relative humidity caused the increasing vapor pressure difference between air and solution surface, thus leading to an increase in moisture removal rate. From the experimental findings, as the temperature of the solution increases from 31.97 degrees centigrade to 34.24 degrees centigrade, the absolute humidity reduction decreases from 11.23 gram per kg to 7.36 gram per kg, that is 34.4% reduction, and the dehumidifier effectiveness decreases from 0.92 to 0.8 respectively. These are the references. Thank you.
Okay, thank you very much. Now it is open for questions from the participants. Anyone who want to ask a question, please unmute yourself and then you can ask that question. Okay, maybe then I'll go ahead and ask the question. Is the presenter present over here?
Yes, sir.
What is your name?
Sir.
Good morning.
Kalpana.
Kalpana, okay. Very nice work. So one question I am having, this one that you are using the flat plate solar collector to provide the heating of this particular system. So what is the typical temperature at which you are getting the hot water from the collector?
Sir, actually, we have done our experiment during May and June. So at that time, we are getting approx 70 degrees, 60 to 70, between 60 to 70 degrees centigrade. And the regeneration temperature which is required for calcium chloride, that is approx 50 to 55 degrees centigrade, which we are maintaining.
Okay. And what role does the temperature of the fluid coming from solar collector play? If the temperature, let's say, drops or it increases, it may fluctuate depending on the solar irradiation also, right? From hour to hour.
Yes, sir. So actually, we are storing that water which is coming from the solar collector in one storage tank, where we are maintaining the temperature of its approx 55 degrees centigrade. And through this storage tank, we are flowing this water into the regeneration tank in copper coil, where its main purpose is to regenerate the diluted calcium chloride solution. Means diluted, it convert it taking moisture from the, means heated the diluted solution of calcium chloride, and air is flowing through that, in the flowing there. So air is taking moisture from this diluted solution, so that it will convert into the concentrated solution.
Right, right.
Yes, sir.
Okay, and one last question. In the last slide, I think figure 11, you have compared your result with Chang et al. And you have shown that your curve is definitely higher than their results. So can you give an estimate of some uncertainty, like in terms of percentage? Is it even greater than the uncertainty? Can you comment on that?
Sir, actually, we did not found uncertainty, but we just simply compare our results from there, because our system is somewhat means their system is bigger than our system, but that calcium, we are using calcium chloride, they are using lithium chloride, and some they are, means we are using solar collector for the regeneration, they are using some electric setup for the regeneration.
Right, right.
So these kind of thing, and one most thing is that we are regeneration and storage tank is same in our case, but they have used some other things.
Okay. Okay.
So we will go for, means we'll find uncertainty also. Okay.
Yes, that would be advisable, because you are doing some measurement experimental work, so you can quickly calculate for one of those points. Then it will be better. Okay.
Okay. Okay. Thank you, sir.
Okay, thank you. So last chance for anyone to ask any questions from the first talk. Okay, if not, let us thank our first speaker. Thank you very much. Now we move on to the good. Now we move on to the next talk, which is titled Experimental Investigation of Elliptical Nozzle on the Concave Surface with a Various Aspect Ratio. And who is the presenter for this particular talk? It is Jay Kumar Joshi.
Yes, sir.
Okay. So please go ahead and play this. So volunteers are present. So I think there was some audio overlap in the previous talk. So please take care of that one if it is possible. And I will request all the participants to please keep their mic on mute during the presentation, and afterward they can unmute to ask the question. Okay. So I request the volunteers, please make sure that there is no background audio. I think in the previous one, there was some audio related. Try to fix that. Please go ahead.
Yes, sir. Yes, sir. That it will not be happening again.
Thank you. Thank you.
I'm Jay Kumar Joshi, and I'm pursuing my PhD from IIT Indore. I'm presenting my topic on experimental investigation of elliptical nozzle on the concave surface with a various aspect ratio. These are the outlines of my presentation: motivation, introduction, flow characteristics of jet for the curved and the flat surface, objective of the investigation, experimental facility, results and conclusion, followed by the reference. So, as you know, the efficiency of gas turbine plays a crucial role in the operating cost in the aviation industry. However, the efficiency of gas turbine is a strong function of maximum working temperature, and metallurgical constraint is one of the defining parameters that limits the maximum working temperature for the turbine. So, one of the way to increase the efficiency is to increase the maximum working limit, but maintain the temperature of blade below the working temperature of material. So it can be achieved with the cooling of blade, and jet impingement has shown one of the promising method for getting the higher heat transfer coefficient compared to the other single phase cooling methods. It can be used for other applications such as combustors for high pressure turbine vanes to maintain the active clearance control of turbine casting and the blade, and de-icing of the aircraft wings. These are the applications of jet impingement on a curved and a flat surface. So as I discussed earlier, it is used in the gas turbine blades for de-icing the aircraft wings, processing of metal form, and electronics cooling for the servo. Introduction: jet impingement has a huge potential for high transfer application due to its simple construction and higher control on parameter during the operation. jet impingement gets a huge attention due to its characteristics of high localized heat transfer for the smaller surface area. Such method usually provides the higher heat flux with respect to the pressure drop in the flow compared to the other cooling methods. In addition to this, we can achieve the uniform cooling for the larger surface area with the multiple jet arrangements. These are the different parameters that affect the local as well as that affect the local heat transfer characteristic of jet. It's Reynolds number, nozzle to plate spacing, inclination of jet, nozzle geometry, the curvature ratio for the curve plate, surface texture, length of nozzle, and the turbulent intensity of the jet at the nozzle. Flow characteristics of jet impingement. It can be divided into three regions: free jet region, stagnation region, and the wall jet region. After jet issuing from the nozzle, it starts losing its momentum due to the entrainment of the surrounding air into the jet. However, the central portion of the jet maintains its momentum up to the certain distance, which is known as a potential cold length. And surface has no influence in the fluid dynamics of the jet in the free jet region. When jet approaches the surface, it starts losing its axial velocity component, and in the stagnation region there is a sudden change in the direction from axial to the radial, and stagnation region is also known as a deceleration region, followed by the wall jet region. When jet impingement on the curve plate compared to the flat surface, there is a change in the fluid dynamics in the wall jet region due to the centrifugal force generated in the boundary layers. This centrifugal force stabilizes the flow in the concave surface. However, for the concave surface, it destabilizes the flow, and that affects the local heat transfer characteristics. This instability leads to the vortex formation in the boundary layer, which is known as a Taylor-Goertler vortices. These vortices are aligned in the flow direction, and two adjacent vortices are rotating in an opposite direction. One of the reasons of increasing the heat transfer for the curved surface is thinning of the boundary layer, and that increases the temperature gradient inside the boundary layer, which result in the higher stagnation heat transfer for the curved surface compared to the flat surface. These are the objective of my present investigation: to investigate the effect of aspect ratio on a local heat transfer characteristic for the jets, study the local heat transfer characteristics in the circumferential as well as in the longitudinal direction, examine the effect of various Reynolds number on the heat transfer characteristics of elliptical jet. Schematic of test facility. We are giving the constant heat flux boundary condition to the plate with the help of DC power source. Air is used as a working temperature, which is supplied by the compressor, and FRL unit is used to regulate the pressure in the whole line, and with the help of compressed air counter we are measuring the mass flow meter. To measure the temperature distribution along the surface, we are using the IR camera, which is based on the thermographic principle. Results and conclusion. As shown in the figure 6, there is a drastic change in the local as well as in the stagnation heat transfer coefficient with a change in a Reynolds number. With increasing Reynolds number from 22,000 to 65,000, the velocity of jet increases. That leads to a higher mass flow rate of jet, and that increases the heat transfer coefficient of jet. Ultimately, it reflects in the higher Nusselt number for the higher Reynolds number. With comparing figure 6a and 6b, it is visible that with increasing the aspect ratio from 2 to 4, there is an increase in the heat transfer coefficient, and the reason is with the increasing the aspect ratio, the induced vortices at the nozzle exit increases, that increase the turbulent intensity, and that result in the higher heat transfer coefficient. As shown in the figure 7, it's compared the heat transfer coefficient for longitudinal and circumferential direction for the two different aspect ratio. As shown by comparing figure 7 and 7b, it is visible that with increasing the aspect ratio from 2 to 4, the difference in the circumferential and the longitudinal direction increases, and the reason is the jet spreading. When jet is circular, or we can say aspect ratio 1, we give the similar heat transfer in the both direction in the circumferential and longitudinal direction. However, with increasing the aspect ratio from 2 to 4 or 1 to 4, we are getting the different heat transfer coefficient in the longitudinal and circumferential direction. These are the conclusion of my investigation. When elliptical jets strike on the concave surface, it maintains its shape for the lower nozzle to distance. Jet spreading of the elliptical jet increases with increasing aspect ratio due to the entrainment of the surrounding air increasing with the increasing the aspect ratio. It is observed that with the increasing the aspect ratio, the difference in local heat transfer coefficient in circumferential and the longitudinal direction increases. These are my references. Thank you.
Thank you very much for your talk. Now it is open for questions. Those who want to ask question can unmute their mic and please go ahead. Okay, so I have a few questions. Jay, are you here?
Yes, sir.
Okay, very nice work. So one thing I wanted to know, this Nusselt number that you have calculated and you have plotted in some of the figures that you have inferred from the temperature measurement. Is that correct?
Yes, sir.
Okay, and for measuring temperature, you are using the IR camera.
Yes, sir.
So can you explain a little bit, like what is the principle behind that? Which surface did you choose and what was its emissivity?
Oh, so sir, we are using SS stainless steel, the thin plate which has a 150 micron sheet, because that we get the lesser temperature difference between the two sided of plate. At one side we are impinging the jet, and from the second side we are measuring the temperature. Again, to measure the temperature, we have to increase the emissivity of the plate which is closing to the camera. So we are using the paint to increase the emissivity. And we have already performed the experiments regarding the paint. It is giving around 0.95 emissivity. We are putting that value in the software, which is already given by the company manufacturer, and that's how we are calculating the temperature.
Okay. And can you share a little bit what is the temperature range that you are getting? Is it like near 100 degree or much higher?
No, sir. It's below 100 degrees. Around, for maximum case, I'm getting around 60-65 degrees.
Okay. So it varies from ambient temperature to about 65 degrees.
Yes, sir.
So once the temperature range you find is not very large, then you must have assumed that emissivity is constant for that temperature.
Yes, sir.
Okay.
Yes, sir.
Okay. Yeah, that makes sense. Nice work. And I think one of the members, you were saying something? Somebody has raised their hand.
Hello.
Yes, please go ahead, Ajay.
Yeah, Jay, I wanted to ask one question from figure 7.
Okay.
There is, I have seen the reduction in Nusselt number for when the aspect ratio is increased for both longitudinal and circumferential. Can you give the reason for that reduction in Nusselt number?
You are asking for the difference, right? Difference between the circumference and longitude. Okay.
No. The Nusselt number variation has reduced when aspect ratio is increased for both longitudinal and circumferential. I think for first one it is 400, starting from 400, and second one it is starting from 300. I think so.
I think I'm really sorry. I think I have sent some wrong images there. There is an increasing that. I think I have misplaced the image. It is increasing.
Okay. So can you give the reason for that increase?
By increasing the aspect ratio, the vortices will be formed, and these vortices will further increase the turbulence intensity, and that will result in the higher Nusselt number, the stagnation rate.
Is there some concept of thermal boundary layer, thinning of some thermal boundary layer there?
It will happen. It will be there because if the curvature is there, but if increasing the aspect ratio, there is no change in the thinning of the boundary layer for that purpose only. If we change the curvature ratio from flat to surface, it will be changed.
Okay.
Thinning will be there with the change in curvature ratio.
Okay. Thank you. I wanted to ask you this question. Oh.
Okay. Thank you.
Okay, thank you, Ajay. Are there any other questions? If not, let us all thank our speaker for giving a nice talk. Thank you very much, Jay. And now we move on to the next presentation, which I think is paper number 200. And the title is Simulation of Hypersonic Flow over the Martian Entry Vehicle using Direct Simulation Monte Carlo Quantum Kinetics Method. So is the presenter? Yes, Shesh, I think is here.
Rightly
Please,
Radhika.
yeah, please go ahead and start this presentation. And I once again request all the participants to please mute their mic and they can unmute at the end of the presentation. Thank you.
My name is Shesh Nayan Dhurandhar and my presentation topic is simulation of hypersonic flow over the Martian entry vehicle using the direct simulation Monte Carlo and quantum kinetics method. This after slide contains background and motivation, introduction, literature review, methodology, results and discussion and Introduction. The re-entry. Re-entry is the movement of a spacecraft from outer space into and through the gas of an atmosphere of a planet. The re-entry spacecraft, the spacecraft which enters into the planetary atmosphere at hypersonic speed. And for the Earth atmosphere, the re-entry occurs at around 100 km altitude, and for the Martian atmosphere, the re-entry occurs at around 80 km.
उसको बंद कर दो.
At very high altitude, when spacecraft returns from deep space, it encounters low density environment. The velocity of the spacecraft is very high, which is around 5.8 to 9 km per second. And high temperature shock layers are generated in front of the vehicle, and due to this high temperature shock layers, the chemical reaction may take place in front of the safe vehicle. In the low density environment, the continuum assumption breaks down and we cannot apply the Navier-Stokes equation. And we should consider the particle nature. And to simulate this type of flow, we use DSMC method, which is the particle-based method used for simulating high Knudsen number flow. And the quantum kinetics method, which is based on quantum vibrational model, is used for chemical reaction in rarefied gas environment. The basic DSMC algorithm is first the set up cell network. The domain is discretized using computational cell. Particles are initialized inside the cells. Particles are moved according to velocity provided at the boundaries, and each particles are indexed and tracked from initial point to the end point. Selection of collision pair and perform intermolecular collision this is the important part where the particles collision pair are selected. Particles are selected and checked for the possible chemical reaction and possible vibrational relaxation and possible rotational relaxation. And the last step is to sample the flow field where the microscopic properties of the particle are used to calculate the macroscopic properties. These are the literature review, and Larsen and Bourganet first introduced the internal energy model where the energy exchange between translation and rotational energy has been explained. And next, the Bird introduced the total collision energy chemical reaction model where modified Arrhenius reaction rate coefficient were used, and the reaction probability depends on the translation, rotational and vibrational energy of the particle. Bird introduced the quantum kinetics model to reduce the dependency of the reaction probabilities, and now the reaction probability dependent on the translation and vibrational energy and dissociation temperature. There was a problem of detail balancing. After the collision, energy were not coming to equilibrium, so Bird introduced detailed energy balance process, and in 2015, Scanlan adopted the QK model and simulated flow over the cylinder in the Earth atmosphere. Next, the methodology. First, we will discuss the vibration relaxation model, and we will discuss the chemical reaction model, which is dissociation, endothermic and exothermic exchange reaction. All the models are implemented in open form software 1.0. First, the vibration relaxation process. Consider a binary collision of particle P and Q. First, we calculate the collision energy of the particle P, which is the sum of relative translation energy and the vibrational energy of the particle. And we calculate the maximum possible quantum vibrational number. And if we check if this maximum possible quantum vibration is higher than this value, then particle will dissociate. If it's not higher than, then vibrational energy exchange. Then we calculate the vibration collision number, which is the function of translation temperature, dissociation temperature, and viscosity temperature index, and reference collision number. And inverse of this vibration collision number is compared with the uniformly distributed random number between 0 and 1. And we select the post-collision vibrational energy state between 0 to I max. And again, the probability is calculated. And if this probability is satisfied, then vibrational energy exchange will take place between particle P and Q. And the same procedure is repeated for the particle Q and all the modes of particle P. Next is vibration relaxation study. To study the vibration relaxation, we have considered a single cubical cell of 10 micrometer size, and we have taken 0.1 million simulated particles, and time step is taken as 10 to the power minus 8. And number density of the species is 5.17 10 to the power 21 molecules per meter cube. Initially, we have set 10,000 temperature for rotational and translation energy mode. And for the vibrational energy mode, we have set 0 Kelvin temperature. And after sufficient number of collision, we can see the equilibrium temperature reaches around 4,360 Kelvin. And this results were compared with the DS2B code. Next is quantum kinetics chemical reaction model. First, we consider the dissociation reaction. Consider a particle collision pair of particle AB and C. We calculate the collision energy as we explained in vibration relaxation process and the maximum possible quantum vibrational level. And if this maximum possible quantum vibrational level is crossed the maximum value of energy level, then particle AB will dissociate. And if particle A and B, the dissociation product, particle A and B, is molecule, then we set vibration and rotational energy to the particle AB, and if it's atom, then we set only translation energy to the particle EB. Next is endothermic exchange reaction. If particle A, B, C, and D are selected for possible exchange reaction, the collision energy of the particle pair is calculated, and we calculate the modified activation energy, which is the product of activation energy and this term 1 plus A T by 273 power P. And the term A and B are parameter for adjustment of activation energy, and EA is the reaction activation energy for the reaction. The reaction probability is calculated using this formula, and as the product is molecule, then we set vibration and rotational energy, and if the product is atom, then we set only translation energy to the product. Next is exothermic exchange reaction. If particle AB and CD is selected for exchange reaction, we again calculate the activation energy, which is the product of activation energy into A T by 273 power B, and we calculate the reaction probability using this formula, and again we calculate the reaction rate. This formula is same for endothermic and exothermic exchange reaction. Next is chemical reaction list we have used for the Martian atmospheric study. We have taken total 8 species, which is CO2, CO, NO, N2, O2, O, N, and C. We have taken 40 dissociation reaction and 7 endothermic and exothermic exchange reaction. Next is pre-strip condition for the spacecraft. We have taken 6.5 km per second entry speed, and number density is 5.17 10 to the power 21. Pre-stream temperature is 140 Kelvin, and Knudsen number for the spacecraft is 0.00042. And the molar fraction of CO2 is 0.97 and N2 is 0.0. The left side figure shows the configuration of the re-entry spacecraft, and the right side is the mass over the re-entry spacecraft. Initially, we have taken 2 million simulated particles, and the time step we have taken is 10 to the power minus. Next, the temperature plot along the stagnation line. The left side of the figure shows when the chemical reactions were not activated, and the right side of the figure shows when the chemical reactions were activated. After including the chemical reaction, the overall temperature reduced to 7,520 Kelvin from 18,314 Kelvin. There is significant reduction in temperature due to chemical reaction, and this result were compared with the CFD result, and we can see that the CFD result shows very low shock layer thickness, and this is the reason due to CFD uses different flow solver and chemical reaction model compared to the DSMC solver. Next is the number density plot. We can see the highest number density observed is the oxygen, and the second highest is the carbon monoxide. And this is compared with the CFD result, and we can see that carbon monoxide number density is almost similar compared to the TSMC result. Next, we studied the pressure and heat flux on the surface of the re-entry vehicle. The left side of the figure shows the pressure on the surface of the re-entry vehicle. Here we can see the maximum stagnation pressure was observed at the stagnation point, which is around 15.4 kilopascal, and it's continuously reducing towards the side of the surface. And in the right side of the figure, we can see the heat flux on the surface of the vehicle. At the stagnation point, the heat flux value is found to be around 125 watt per centimeter square, and its value is increasing due to the curvature surface and again reducing towards the side of the surface. We have done the study, we have drawn some conclusion. We have proposed a QK model for the Martian atmosphere chemical kinetics. Reaction rate for equilibrium as well as non-equilibrium condition has been studied. Simulated the flow over the re-entry vehicle. The results were compared with the CFT, and we found that the concentration of the CO is the same order as the CFT result. And we found the convective heat flux at the stagnation point is 125 watt per centimeter square, and the maximum pressure found at the stagnation point, which is around 15.4 kilopascal. In this study, we have not included recombination reaction. The next task is to include the recombination reaction and to simulate the flow over the re-entry vehicle. And this is it. Thank you.
Okay, thank you very much, Shesh. Are you present over here?
Yes, sir.
Okay. Very nice work. So let us open it up for questions from the audience members. If anybody wants to ask question, they can unmute their mic and ask the question. Yes, I think somebody has raised their hand. Ajay, please go ahead.
Hello. Yes, sir. I have a question from slide number 20. He's showing that when the chemical reactions are considered, there is a sudden reduction in temperature behind the shock. I just want to know what is the percentage of temperature reduction?
I have already shown that it's around 18,000 Kelvin when there was no chemical reaction, and when the chemical reaction were activated, it's around 7,500, means 11,000 Kelvin temperature reduction. So for the different cases, it will vary. So just calculate the percent.
Okay. And I think you have not considered the comparison of heat flux for without chemical reactions and chemical reactions.
Yeah, I have not shown here.
Okay. Can you tell me what is the difference over there?
It was around 200 watt per centimeter square, and when chemical reaction were activated, it was around 125.
Okay. And what is for surface pressure?
Surface pressure, I cannot say right now. Actually, I don't remember that value.
Okay, no problem. Thank you.
Oh.
Okay, thank you. So I'll ask one last question if there are no more questions. That how long does generally this re-entry period last?
It depends upon the speed, sir. So it's around 3 to 5 seconds maximum.
Okay. So it must then, if the period is very short, then it means that the whole thing happens like a transient analysis. So has that been taken into account, or are you doing a steady state analysis?
Sir, it's transient state.
Okay.
All the chemical reaction I will consider for non-equilibrium condition. So it completely transient state.
Okay. Are there any more questions? If not, let us thank Sesh on behalf of all the participants and conference organizers. Thank you very much. Now we move on to our next talk, which is paper number 204. And I think Akriti must be here to present. The title of the paper is Impact of COVID-19 Lockdown on the Aerosol Levels in India and Solar Irradiance Forecasting using Weather Research and Forecast Model and Satellite Remote Sensing. Please go ahead.
The topic of our presentation is Impact of COVID-19 Lockdown on Aerosol Levels in India and Solar Irradiance Forecasting using WRF Model and Satellite Remote Sensing. So India has a huge power generation capacity as it receives more than 5,000 trillion kilowatt hour per year of solar radiation, which is far more than its total annual energy consumption. The energy utilization can be carried out in various ways, and smart cities require smart energy in which contribution of solar energy is significant for reducing conventional energy dependencies. Among the solar energy technologies, PV and CSP installations have seen tremendous growth, providing carbon-free and renewable electricity. It is a well-known fact that the solar radiation reaching the Earth's surface is attenuated by various atmospheric constituents, among which clouds and aerosols are the major contributors. Aerosols scatter and absorb solar radiation in the atmosphere. High levels of air pollution block sunlight, which reduces solar panel performance. COVID-19 lockdown led to a reduction in aerosol levels around the world, and the drop in air pollution levels led to clearer air, which in turn led to an increase in solar irradiance, which resulted in an increase in PV yield. So this study analyzes the aerosol levels during the lockdown, its effect on solar irradiance, and its impact on the revenue generation from solar-based plants. So the major nationwide lockdown in India was held from 25th of March to 14th of April, and this analysis is basically focused on this particular period. So here we present the data and methodology. So the analysis period that we have chosen for the WRF simulation is from 22nd to 31st of March 2020. The study region selected is Delhi. The inputs that has been used are CAMS AOD and GFS data. So GFS is a global forecast system, which is a global forecast model that has been used for running the mesoscale WRF model. And the output that is generated from the simulations include GHI and DNI, that is global horizontal irradiance and direct normal irradiance. So as can be seen from the flow chart, CAMS aerosol optical depth was used to monitor the aerosol levels, and the MODIS 5-year climatology was used to analyze the historical aerosol patterns. So the WRF day-ahead forecast for the low aerosol period was generated using CAMS AOD as input, and the output was GHI and DNI estimations. And this analysis was ended with a financial analysis. So here we have shown the WRF configuration. So WRF uses an ARW solver, which is based on the integration of compressible non-hydrostatic Euler equations. The flux form is used based on the conservation of mass, momentum, and energy. Initialization was done with the GFS data at 0 UTC with a spatial resolution of 0.25 degree in latitudinal and longitudinal directions, and a temporal resolution of 3 hours. The initial and boundary conditions were obtained from the GFS model, and the domain was divided into 71 cross 63 grid points in latitudinal and longitudinal directions with 33 vertical levels. So in the table we have presented the physics that has been used, the various schemes that were chosen. So for microphysics we have chosen New-Thomson scheme, and for cumulus parameterization TK scheme was used, followed by a rapid radiative transfer model for shortwave and long-wave radiation. And the simulations were enhanced by incorporation of CAM-COD into the model. So here AOD variation has been shown for the months of March and April, and it can be seen that during lockdown, that is late March and early April, CAM-COD was well below the mean modest AOD, and before lockdown in April end, the CAM-COD was mostly above the mean modest AOD level. So the average AOD during pre-lockdown was found to be around 0.64, and in March end it was found to be around 0.41, which was a 35% decrease. And in early April it was found to be around 0.5, which was a 22% decrease. As compared to the modest 5-year mean monthly AOD, towards the March end, there was a decrease in AOD of 0.14, which is 25% decrease as compared to the modest AOD. And in early April, the decrease was 0.04, which was an 8% decrease. So here a GHI and DNI plots is shown for the entire domain in the beginning of lockdown and after a few days in April, towards the end of March. And it can be seen that there's a significant increase in radiation throughout the Indian region. So here are the results of the WRF model for GHI and DNI estimations, which are also compared with the BSR and GHI of 2018. And the WRF was run with two AOD inputs. One is the CAM-COD and the other is the modest COD. And the output generations are GHI and DNI. So it can be seen that the difference in the CAMs versus modest based WRF generations, the average difference was found to be around 30 watt per meter square, which is a 3% GHI increase, and the maximum difference was found to be around 49 watt per meter square, which is a 5% increase. Similarly, in the case of DNI, the difference between the CAMs and modest based DNI was found to be around 92 watt per meter square, which is a 14% decrease, and the maximum difference is found to be around 149 watt per meter square, which is a 19% increase. So here we present the financial analysis. The assumptions that were made has been listed here. So it can be seen that towards March end, the maximum energy potential from the CSP and PV plants are 0.89 and 0.9 kilowatt hour per meter square, with an average energy potential of 0.81 and 0.69. So the maximum revenue generation from CSP plant was found to be around 4.34 Indian rupees per meter square, and it was 4.52 in case of PV plants. So the revenue increase in case of CSP plant was found to be around 0.17, and in case of PV plants it was found to be 0.37. So we did the analysis for a 1 megawatt total installed capacity, and the daily average revenue increase was found to be 3,500 Indian rupees for CSP installations and 7,500 Indian rupees for PV installations. So the lockdown showed an average increase in GHI of 3%, and in DNI it was 14%. The revenue increase for a 1 megawatt plant was found to be around 3,500 Indian rupees and 7,500 Indian rupees for CSP and PV plants respectively. A similar ground-based measurement was made for Delhi for the same period that revealed that the PV installations in March and April received more than 6% energy in total than in previous years. So replacing the sources of air pollution by solar powered technologies will result in cleaner air, which in turn will benefit the solar powered devices, and much greater benefits are expected for human health. Thank you.
Thank you very much, Akriti. Now it is open for questions from the participants. Okay, so I have a few questions. This is a very interesting study. Akriti is here. Hello. I can see her name. Akriti, do you want to unmute? So if you are here, then maybe I'll ask a few questions. I think it is showing in front of you that your mic is still muted. If you want, you can unmute your mic so that you are able to answer the question. Or maybe she has got disconnected. Are you still there? Okay. Are any of the other co-authors present from this paper? Okay. I think there is some connectivity issue perhaps. So if the participant is not present, then we will move on to the next paper, which is paper number 205. So this title of the next talk is on creeping flow of a yield stress fluid past a square cylinder in a channel.
Good morning to one and all present over here. I am Anshuman Verma from Department of Chemical Engineering, IIT Ropar, and I am here to present our paper on creeping flow of yield stress fluid past a square cylinder in a channel. This is the overview of my presentation. I will first introducing what these yield stress fluids are, then I will briefly discuss the motivation behind our current research work, then I will discuss our research approach and main findings in detail, and then finally I will conclude this presentation by summarizing all these results. So let's get started. Yield states or viscoplastic fluids, or so-called viscoplastic fluids, are the fluids which show both elastic solid-like characteristics and viscous liquid-like characteristics. They are encountered in wide range of applications, starting from food items like bread and jam, chocolate, ketchup, mayonnaise, to cosmetic products and hygienic products like shaving foam, toothpaste, etc. All this come under the category of viscoplastic fluid. In addition to this, these fluids are also encountered in wide range of industrial applications. For example, paint, cement paste, mineral slurry in mineral beneficiation, while in oil recovery, oil suspensions act like viscoplastic fluids. In nature also, lava, there are several examples. For example, lava flow out of volcano and mudslide. All these examples in one way or other involve flow of viscoplastic fluids. So the next question we ask is how these yield stress or viscoplastic fluids are different from Newtonian fluids. To answer this question, we take two different fluids, fruit juice and tomato ketchup, and see their flow behavior. Fruit juice flows out of the container freely into the glass, while tomato ketchup flows only when a certain minimum stress is exerted on the container. So how do we characterize this flow behavior? To do so, we plot the rheogram of both these fluids, and we see that in case of Bingham plastic fluid, there exists a minimum threshold, a stress level known as yield stress, below which the material does not shear and acts like an elastic solid. Once this applied stress exceeds the yield stress, these materials may viscoplastic materials may either exhibit constant shear viscosity like this meat extract solution, or it may exhibit shear thinning viscosity like this carbopol solution. So this table alongside shows the yield stress of some of the common products, and we can see that these yield stress range from 1 to 2 orders of magnitude. And we can thus say that presence of yield stress makes this Bingham plastics fluid differ from Newtonian fluids. So, coming to the motivation behind our work, the flow of viscoplastic fluids past solid objects subjected to bounded and unbounded flow conditions denote idealization of several important industrial applications. For example, continuous thermal treatment of foodstuffs, design of novel heat exchangers in which tubes of different cross sections other than circle are used, processing of granular particles, support structure exposed to flow stream of fluids, like in marine engineering applications. In addition to this, there's considerable theoretical interest also uh, in the study of flow of yield stress fluid past geometries with sharp cross sections. So, coming to our research methodology and finding, to predict the behavior of flow dynamics in 2D creeping flow of Bingham plastic fluid past a square cylinder, all the governing equations have been solved assuming a steady state condition. Finite element based numerical methodology has been employed to solve the governing differential equations, and in order to avoid the inherent discontinuity in the ideal constitutive Bingham equation, we have used modified model proposed by Papanastasiou in the current numerical scheme. The numerical results include a study of flow kinematics in terms of velocity, spatial velocity variations along the lines of symmetry, vertical axis of symmetry, and the horizontal axis of symmetry. Along with that, we have studied in detail the morphology of yielded and unyielded regions and the effect of Bingham number on it. And we have also studied the effect of Bingham number on drag coefficients and proposed correlations connecting these two parameters. Bingham number has been varied over wide range over 6 orders of magnitude from 1 to 10 to the 6, beyond which no further influence of Bingham number was seen on any of the kinematic parameters. So let's come to our problem statement. We have a square cylinder of side length D, which is infinitely long in the z direction. Flow past which Bingham plastic fluid is flowing with negligibly small velocity, so that the inertial effects can be neglected. This square cylinder is placed in unconfined domain of side length 2L, and since it is a creeping flow symmetric problem, we can solve this all these governing differential equations along the axis of symmetry ED and AB. And we can solve this entire problem by solving the problem in 1/4 of the domain, and we have chosen OBCD as our computational domain in this case. So these are the assumptions: steady state creeping two-dimensional incompressible flow with governing equations. These are the ideal constitutive Bingham equations, and these are the boundary conditions. We have employed no slip boundary condition on the cylinder walls, and we have taken symmetry boundary conditions on the vertical as well as horizontal axis of symmetry. Bingham number, which is the ratio of yield stress to viscous stress, has been varied from 1 to 10 to the 6. So now let us come to see the discontinuous nature of Bingham plastic model. Owing to the presence of yield stress, both fluid and solid-like regions coexist in the flow domain simultaneously. It can be clearly shown in this photograph, where mud suspension is flowing in a channel. In this lateral region, in the vicinity of this channel wall, the applied stress is greater than the yield stress, and therefore the fluid is sheared. But in the central broader region, applied stress is less than shear stress, and therefore the fluid is not sheared and it is moving with constant plug velocity. So this ideal Bingham constitutive equation shows discontinuity at tau is equal to Bingham number, and as such cannot be employed directly for any numerical computation. To alleviate this problem, we are using regularization method proposed by P.C. Papanastasiou, in which this regularization parameter small m takes care of the unyielded region by approximating them as extremely viscous, and as m tends to infinity, as this m value tends to infinity, this Papanastasiou model reverts back to Bingham plastic model. And the figure on the alongside, we have shown the the effect of non-dimensional regularization parameter capital M on the location of rigid zones. We see that beyond capital M is equal to 10 to the power 4, no further influence is seen on the location of rigid zones. Therefore, M is equal to 10 to the power 4 has been employed in all the computations in this work. So finally, coming to our results, we see that when Bingham plastic flows past a square cylinder under negligible inertia, fluid-like seared and solid-like unseared regions coexist in the flow domain. Three different rigid zones can be clearly deciphered. Zone 1 is located far away from the cylinder surface and is moving with constant plug velocity. Two triangular regions denoted here by zone 2 adhere to the cylinder surface on the upstream and downstream side, while two rotating zones designated as Zn3 are present on either side of the cylinder across its abscissa. And then this is the velocity profile. This is the y component velocity along this horizontal plane of symmetry, and in this small seared region we can see there is a steep velocity gradient, and in this unseared region this is the flat plateau. Again in this small unseared region this velocity reduces back to free stream velocity. Similarly, we can infer the graph below. This graph has been plotted. This velocity profile has been plotted on this vertical axis of symmetry, and we can see that on the surface of the cylinder velocity is 0, and in this a small seared zone, this is varying significantly from 0 to finally reaching free stream velocity in zone 1, this value. So finally coming to drag coefficients. Drag coefficients are very important engineering parameters, and they have been studied here for wide range of Bingham number from 1 to 10 to the power 6. And we see that in the absence of inertia, drag coefficients are functions only of Bingham number, and it is inversely dependent on Bingham number, as can be seen from this shape of the graph, which is kind of rectangular hyperbola. So based on the data of this graph, we have correlated Bingham number and drag coefficient by a well-known approach in which viscous effects and plasticity effects have been separated from one another. And as Bingham number approaches infinity, drag coefficient approaches limiting value of 17.70, and the inverse of this limiting drag coefficient is defined as stability coefficient, which denotes the condition at which cylinder cannot settle on its own bed, and the weight of the cylinder is balanced exactly by the drag force in the upward direction, and the cylinder cannot settle on its own weight. So this Bizy value, this present Bizy value has been compared with other literature value, which are mainly for circular cylinder, and in this case we see that this drag coefficient has higher value in case of square cylinder than in case of circular cylinders. So finally, coming to the summary of our work, this study presents the creeping flow of ill-stressed fluid past square cylinder in a channel over wide range of Bingham number from 1 to 10 to the power 6. The results are based on Papanastasiou model and yielded and unyielded regions flow kinematics drag coefficients along with stability criterion are shown in this work. The growth of unyielded regions become independent of Bingham number at high values of Bingham number, and drag coefficients are found to be inversely dependent on Bingham number, and correlation for total as well as pressure drag coefficients has been proposed as a function of Bingham number. The stability criterion for square cylinder has been determined as Bizy is equal to 0.058. So thank you very much. This ends our discussion, and I will be very happy to try answering your questions. Thank you.
Okay, thank you very much, Anshuman, for a very nice talk. Are you present here to take questions?
Sir.
Okay. So now I request our participants, whosoever wants to ask question, they may unmute their mic and feel free to ask questions one by one. So are there any questions from the participants? So I have a few questions. Maybe I'll go ahead and ask that. What the later part of your talk, you showed a graph which is plotted between the drag coefficient and the Bingham number.
Yes, sir.
So why does that, can you give a brief explanation at a very high Bingham number? Why does the drag coefficient become almost a constant?
Because sir, at high Bingham number, this rigid zone increases in size, leading to the confinement of fluid. This unyielded fluid is present in very narrow region beside the cylinder. Therefore, drag coefficient reaches its limiting value at high Bingham number.
Okay. And this is expected irrespective of the shape of the cylinder. For example, if instead of square, if it was circular, elliptical, or rectangular.
Yes, sir. Yes, sir. It is a classical result, and it is geometries.
Okay. Okay. And one last question I wanted to ask: what was the motivation of choosing the square-shaped cylinder? Is it something that you are inspired by some industrial application? Why not
Sir,
the circular cylinder?
yeah. Sir, actually, this square cylinders, like several food items like carrot slices and potato slices, this can be modeled as square bars, and these are most often placed in some polymer solutions which act as viscoplastic fluids. So we wanted to know the effect of viscoplastic fluid past this flowing past these square food items.
Okay. Okay. And you had mentioned that the velocity was taken as negligible. So if we want to see in terms of Reynolds number, it is very, very low Reynolds number, right? Because inertial forces are low and mainly highly viscous forces are there.
Yes, sir. Yes.
Okay. So it may so be, maybe, can we also say that when the Reynolds number is extremely low, then the shape of that particular cross section doesn't really play a difference make a big difference as well? Is it correct to say that?
Yes, sir. It is correct. But the main effect is on Bingham number. Bingham number as the Bingham number increases, this fluid becomes more and more confined.
Right.
And
Right.
yeah.
Yeah. Thank you. It's a very interesting results you have presented. So let us thank our speaker once again. And with that, I don't think there are any other talks in this particular session. So I also thank all the participants for joining in. And I think the next session will probably start as per the schedule at, I think, 11 o'clock. So
Yes.
we can all reconvene maybe at 11 o'clock. So now the volunteers can take over. Thank you.
We thank Professor Himanshu Tyagi for chairing this session. Our next presentation session will start from 11. I request everyone to please join this session.
Okay. Thank you.
Vous allez écrire à l'instant.
Yes, Miss Akriti and Muthu, you have raised your hand. Please tell me what's your query. Hello.
Hello. Sir.
Yeah. Please tell me.
I am Muthu Saravanan. Yeah, I am available for presentation. Actually, my
Okay.
session is there in this.
Yeah. It will about to begin. Yes.
Okay. Thank you.
Thank you.
Thank you.
So you can lower your hand because it will be confusing when the session chair will join.
Yeah, good morning, all of you. Hello.
Hello, sir. Yes,
Good
sir.
morning. Good morning.
Yeah,
Good morning, sir.
this is Dibakar Rakshit from IIT Delhi. So I reckon I am supposed to chair this session, which is starting at 11 o'clock in Hall 3, if I'm not wrong.
Yes, sir.
Okay. Yeah, so I'm already in. So let me
Okay.
know.
So on the behalf of FMFP, we welcome you. We welcome Professor Dibakar Rakshit.
Thank you.
And I request Muthu sir and Akriti to please lower your hand.
Okay. Lower your hand.
You will get the option on the top of your screen.
Top of the screen. Okay.
Sir, if you allow, then I can start the session.
Yes, sir.
Yeah, please go ahead.
Okay, thank you, sir.
Hello.
Hello everyone, I am Muthu Saravanan. I am working as a scientific officer in Indira Gandhi Center for Atomic Research, Kalpakam, and I am pursuing PhD in Homi Bhabha National Institute. The topic of my presentation is numerical investigation of sodium spill spreading on the floor surface under non-isothermal conditions of pool fire scenario. Liquid sodium is used as coolant in phosphoidal reactors due to its excellent nucleonic and heat transfer properties like high thermal conductivity, low neutron moderation, low neutron absorption cross-section, and less induced radioactivity, etc. But the major disadvantage is its reactivity with atmospheric oxygen, and hence the accidental coolant leaks from the heat transfer circuits of FDR can cause sodium fires. The combustion heat released from sodium fire can increase the temperature of cell gas and structural materials in reactor cells, and the rising gas temperature can cause pressure buildup in enclosed cells. Further, the sodium combustion products are released as aerosols, which are corrosive in nature and harmful to the human health. So, the analysis of sodium fires is important in the safety evaluation of SFRs. In general, two types of fires occur in the reactor systems, namely pool fire and spray fire. Among this, spray fire can increase the cell gas temperature and pressure in a short duration due to the higher burning rate of sodium in spray droplet from combustion. On the other hand, pool fire can continue for a longer duration depending on the amount of sodium leaked and the surface area of the pool, and hence the thermal effects on the cell structure and structural materials of the plant can be more pronounced in a pool fire. So the analysis of sodium fire events is essential to evaluate the consequences of different modes of sodium fires for the effective implementation of various protective measures. A typical pool fire scenario is shown in figure. Liquid sodium leaked from the heat transfer circuit falls on the cell floor, spreads on its surface, and burning occurs from the ensuing pool surface. The consequences of pool fire scenario depends on the exposed surface area, which will be decided by the extent of pool spreading. So the analysis of sodium spill spreading characteristics is important in the evaluation of pool fire consequences. In the present work, the spreading characteristics of liquid sodium spills on the cell floor surface have been analyzed using a 1D integral model. Model for liquid sodium spreading on floor surface. The figure shows schematic of the sodium spill scenario considered. The liquid sodium leaking from the spill source falls on the floor surface and spreads laterally in radial direction. Simultaneously, spreading pool loses certain mass due to sodium combustion at the pool surface. Some part of the combustion heat is received by the pool and the remaining energy is transferred to the surrounding air. Also, the floor surface beneath the spreading pool receives the heat energy from hot sodium. The 1D integral model considers spreading sodium as a circular pool of average height, and its lateral spreading in radial direction is evaluated by solving mass and momentum balance equations. The thermal interaction between the spreading pool, floor surface, and atmosphere has been modeled based on the lumped parameter heat transfer equation. Governing equations of the pool spreading model. Mass balance equation. The mass balance equation of spreading pool is based on the rate of sodium mass addition to the pool from the spill source and the removal rate of sodium mass from the pool surface due to burning. The mass loss due to pool burning has been evaluated from the burning rate of sodium pool fire under atmospheric condition, that is around 35 to 40 kg per meter square hour. Momentum balance equation. Momentum balance equation for the spreading pool is based on the gravity inertial forces and the resistance due to fluid friction between pool base and the floor surface. The average pool height is evaluated from the ratio between pool volume and its surface area. The minimum pool height at the leading edge is obtained based on the viscous effect of the spreading sodium. Based on the ratio between the minimum pool height and the average pool height, the model could account the depth profile on the spreading pool. The friction at the pool bottom is determined based on the flow conditions, that is laminar or turbulent, using the correlations of shallow layer flow. The criterion for laminar turbulent flow transition is decided by the critical Reynolds number. Heat balance equation. A lumped parameter equation considering simultaneous heat addition and heat removal rates from the spreading sodium has been used to evaluate the mean temperature of pool. The spreading pool receives the combustion heat generated from sodium fire at the pool surface and also sensible heat of the leaking sodium. The heat of combustion value for sodium air reaction is around 9500 kJ per kg of sodium burned. The sodium pool loses the heat energy into the surrounding air by convection and radiation, and heat transfer to the floor surface occurs by the conduction. Heat transfer coefficient between the burning pool surface and surrounding air is evaluated using the semi-empirical correlation for turbulent natural convection in upward facing horizontal flat plate. The heat transfer from hot pool to the floor surface is evaluated based on the 1D transient heat conduction in semi-infinite body. Using this developed model, the spreading behavior of liquid sodium spills has been investigated under the isothermal and non-isothermal conditions, and based on this, the influence of heat transfer on the hydrodynamics of sodium spreading has been brought out. Solution methodology. The system of ordinary differential equations, that is mass, momentum and heat balance equations, is solved in a coupled way along with other constitutive equations. The fourth order Runge-Kutta method has been used to get the numerical solution. The explicit iterative scheme has been implemented using a suitable constant time step value along with appropriate initial conditions. For isothermal spreading cases, the heat interactions between the spreading pool and surroundings has been neglected, and the simulations were carried out at a constant pool temperature specified initially. In this case, the solution is obtained from the mass and momentum balance equations without using the heat balance equation. Validation of the model. The spreading model has been validated using the large-scale water spreading experimental results available in literature. In these experiments, water at ambient temperature has been released up to 1000 kg per second leak rate from the bottom of the test vessel and allowed to spread over a distance of 10 meters on a plain concrete surface. As the experiments were conducted at the ambient temperature, the isothermal spreading is considered for this simulation. Also, the evaporation rate of water has been taken as 0 due to its very low vapor pressure at normal atmospheric temperature. A constant time step value of 0.01 second has been chosen, and the iterations were continued till the pool radius reached 10 meter distance. In the experiment, waterfront has reached 10 meter distance in 4.7 seconds, and the model estimated value is 4.8 seconds. Further, the time varying pool radius estimated by the model is found to be in very good agreement with the experimental results. The maximum deviation between the model predictions and the experimental value of pool radius at different times is within 10%. Analysis of sodium spill spreading. Spreading of liquid sodium spills on the floor surface under pool burning condition has been analyzed using the numerical model developed. The leak scenario chosen for this analysis represents the release of liquid sodium from secondary circuits of SFR due to double-ended pipe rupture event, which can occur in the pipelines of size 100 MB or smaller. This event can continue for several minutes, up to 20 to 30 minutes at a leak rate of few thousands kg per hour, until the detection of leak and corrective actions have been initiated. The subsequent spreading and pool formation on the floor surface under sodium burning condition has been investigated using this model. For non-isothermal cases, the thermophysical properties of liquid sodium has been evaluated as a function of pool temperature. Whereas for the isothermal cases, the properties of sodium has been evaluated at the temperature of leaking sodium, that is around 773 Kelvin. The properties of concrete have been used for the floor material. The time step value used for this analysis is 0.05 seconds. The spreading model has been used to evaluate the time varying pool radius, temporal variation of pool temperature, and equilibrium pool area for various leak rates of sodium. The characteristic parameters estimated by the model for different leak rates of sodium are given in table. For the chosen leak scenario, the spreading sodium can attain a maximum area called as equilibrium pool size which is dictated by the balance between the burning rate of sodium and its leak rate from the source. The analysis result shows that the equilibrium pool size reached by the spreading sodium increases with the increasing leak rate. Also, the time for equilibrium pool formation increases with the increasing leak rate of sodium. Further, the temperature of equilibrium pool reached around 1080 Kelvin and it is in line with the steady state temperature of stagnant sodium pool burning in atmospheric air. Further, comparison of time varying pool radius and equilibrium pool size evaluated for different leak rates of sodium under isothermal and non-isothermal spreading conditions shows that the influence of heat transfer on the spreading behavior of burning sodium pool is negligible. So based on these results, it can be concluded that the non-isothermal effects can be ignored for burning sodium pool spreading on the floor surfaces like concrete considered for this analysis. So these model predictions are useful for the analysis of sodium pool fire scenarios pertaining to SFR safety evaluation. Conclusions. Spreading of liquid sodium on the floor surface under pool burning condition has been analyzed using the only integral model for pool spreading. The time varying pool radius, temporal variation of pool temperature and equilibrium pool size have been evaluated for different leak rates of sodium under isothermal and non-isothermal spreading conditions. Analysis results have shown that the equilibrium pool size and time for pool formation are less influenced by the heat transfer effects associated with the spreading of burning sodium pool. Based on these results, it can be concluded that the non-isothermal effects of sodium pool spreading can be ignored under burning conditions. The model predictions are useful for the analysis of sodium pool fire scenarios pertaining to SFR safety evaluation. Thank you.
Thank you, Mr. Muthu, for your presentation. So it was, quite detailed. So I now request from the guests over here to ask any questions if they have, or then maybe I will ask a couple of questions. You can raise your hand. Okay, so I understand then there are no questions. So this is a very good study which can be like in the periphery of nuclear reactors. It is having a lot of like applications. So do you think other than that we can employ this spread of liquid sodium or any low Prandtl number fluid? Can this model be applicable to other low Prandtl number fluids also? That is my first question.
My understanding is actually this low Prandtl number fluids, mainly that heat transfer effects we have studied here.
Okay.
Heat transfer effects are found to be negligible for this sodium case. And what we have found is this thermophysical properties, whatever variation is happened because of heat transfer, this can be neglected actually in this case. So it is possible because with the hydrodynamic effects are main parameters influencing the spreading. So it is possible to include the low Prandtl number fluids also using this model to analyze this.
Okay. Now my next question would be how accurate it is to assume the system to be lumped parameter, like you start lumped parameter analysis, right?
Yes,
so
yes.
That was something which I wanted to.
Because sir, this especially this low thermal conductivity of sodium is very high compared around 63 watt per meter Kelvin. It's thermal conductivity. So what we assumed is because of this there will be no radial as well as depth-wise temperature variations. So we can assume a constant temperature lump.
So that's single. Why lumped.
Yes, okay. Lumped. Yes.
Okay. Yes. And my last question would be, means it is a comparison of two conditions, like one isothermal and non-isothermal. You told that isothermal is good enough to go ahead. So was there any experiment conducted? Or it was
sir, we have small scale experiments in the literature. We have validator also. In that actually, that we have not shown here actually.
Okay.
That is a constant temperature assumption I have taken around leaking temperature 1000 Kelvin. We can take and we have analyzed. We have found it is very nicely matching. So what we have tried is if we include the temperature variation also, what sort of property variation is happening, and that is how it is influencing further the spreading behavior we want to see. For that we have carried out this analysis. So it shown that actually that whatever constant temperature assumption we have earlier used, that is reasonably valid, and it is possible to analyze this sodium spreading scenario with a constant temperature modeling itself.
Okay. So I think I am fine with the answers which you have given. Thank you for the presentation. So there is one, I think, query from Mr. Siva K. Mathina. So yeah, Mr. Shiva,
yes,
you
sir.
can go ahead, please.
Hello.
Yeah, you can ask a question.
Sir, my question is, have you validated your results with any experimental data? Sorry if I ask a question.
One is actually water with water spreading experiments. That numerical model we have validated, that we have shown here. It is nicely predicting, but sodium case also we have validated, but that results we have not shown, actually is yet to be presented. But in this case actually water I have shown mainly. Yeah, we have validated. Yes.
In your paper you said that this is sodium pool fires, but
yes.
Density of the sodium is different than the density of water. No? How can you justify that these results are water results are?
Yeah, they are more or less same. Water around 1000 kg per meter cube, whereas in
Yes.
sodium around 850 around. So with respect to that, it is not. It is matching actually. Hydrodynamic properties of sodium as well as water, they are both are almost same. Viscosity and density. These two are. So these are the main parameters which will affect the spreading behavior. So
and what are the uncertainty levels in your simulations and compared to the experimental results?
Uncertainties, excuse me.
Your results.
Yes.
You are validating with some experimental results, na? What are the levels?
Yeah, water case I will discuss. Water case, what we have found is more or less the spreading radius, whatever with time varying radius, that is coming within 10% actually.
What is the experimental uncertainty?
Experimental uncertainty, actually, that is not discussed in the literature, but still we could compare.
Yes, sir. That's what. Without saying the benchmark results, whether it is 10% or 5%, we can't justify that whether these results are accurate or not.
Okay.
First, we need to say this is the experimental uncertainty. Then our results are within that levels.
Mr. Shiva, I think these are preliminary studies which has been done with water, and it is fair enough to go ahead with the sodium results, which Mr. Muthu is saying that already it has been carried out but not presented over here. And then regarding the comparison for the water with sodium, I think this is on the right direction because it is conservative result. You can see the density which means sodium is having and water is having. Sodium is having lesser, but not that lesser. So I don't think the results will be very much away from the water results, if at all means it has been it is to be presented or to be analyzed later. But I think that this is the right direction to go ahead with the study which they are doing. But maybe Mr. Muthu can comment on a bit of uncertainty in the experiments which has been carried out, so that maybe Mr. Shiva can be a bit more convinced. Yeah, thanks.
Thank you, sir. Thank you very much, sir. Thank you.
Thank you, sir.
So I think there are no more questions, so I can request the next presenter to come up with their presentation. Thank you.
Yes, and yes, sir.
Good morning to the respected chairperson and the audience. Title of my manuscript is Effect of Longitudinal Translation of 2-out type vortex generators on wake modifications in fin tube heat exchange. This is the presentation outline. Let me first begin with the motivation and the application. In heat exchanger industry, heat transfer enhancement is an essential way to control the unit cost. It helps in reducing both material and manufacturing cost, and it also helps in improving the compactness of the system. Fin tube arrays is a commonly used design. These heat exchangers involve heat exchange between a gas and a liquid. Overall thermal resistance in these heat exchangers is dominated by the gas side. That is why lowering gas side resistance is key to improve their effectiveness. Low heat transfer coefficients associated with the gas flows necessitates the use of extended surfaces. In gas to liquid heat exchangers, effectiveness of such heat exchangers does not increase much until its gas side thermal conductance undergoes large augmentation. A large fin area is affected by tube wake, and the flow separation is a common occurrence on the gas side. Thermal management of the wake region is essential to improve the effectiveness of such heat exchangers. Incorporating longitudinal vortex generators is an effective way of passively curtailing the occurrence of wake region. The schematic diagram here shows you a pair of vortex generators which are deployed on a fin, and such pairs are deployed in the downstream of tubes in a fin tube array. Percentage augmentation in gas side heat transfer coefficient is found to depend on the number of generator rows in the flow direction. Generators facilitate thermal augmentation by invoking all three mechanisms of passive heat transfer enhancement, which involves creating developing boundary layers, swirl in the flow, and flow destabilization. Degree of thermal augmentation as well as pressure loss increases with the generator area. Generators are instrumental in increasing the vorticity, which manifests as rise in temperature gradients and hence the heat. Among various types of generators, two-out type arrangement is preferred, designed for the wake management because they can direct the approaching flow behind the tubes. Generally, winglets are either rectangular or triangular in shape, and it has been observed that under same area constraint, triangular winglets are more effective than the rectangular ones. Winglet length should be neither too large nor too small, and the winglet location should be mindfully selected as their ability to modify the wake region depends on the position around the tube. Let me state the objectives. In this computational study, delta winglet type vortex generators with two-out arrangement are adopted. Since spatial positioning of the winglets has a critical role in determining the degree of augmentation, the streamwise position is changed in discrete steps to analyze the effect of its position on the wake management. For a wholesome study, generators are deployed at two different cross-stream. Since this is a pure computational work, so let me now discuss the mathematical formulation. We have conducted three-dimensional numerical simulations. Flow is modeled as steady, incompressible, turbulent. The effect of turbulence on the mean flow is modeled by using popular two-equation model, which is K epsilon RNG model. Governing equation discretized by finite volume method, and the simple algorithm is used for the pressure velocity compounding. The governing equation solved by using commercial CFD. The governing equation with index notations are shown here. The first equation continuity, second is momentum, and the third is energy equation. Reynolds stress term, the last term in the momentum equation, is obtained by using business hypothesis. There are two more governing equations which cater to the turbulence modeling. The first one is turbulent kinetic energy, and the second is turbulent dissipation rate. The constants used in these equations are the standard values available in the literature. Multi-block hybrid approach is used to check the mesh quality as well as density. Second order upwind scheme is used to model the convective terms. Effective buoyancy forces and the viscous dissipation are disregarded. Thermophysical properties of the air are treated constant, and the tube wall is assumed isothermal. Heat exchange through the fins is modeled as conjugate heat transfer, and convergence criteria is shown here in the slide. Let me first introduce you with the geometric model. So we have an array of fins with holes in it. The winglets are erected behind each hole, and a tube bank is going to be inserted in these holes. So here I'm showing you the fins with the bank of tubes. So this is after assembly. This is the schematic of the diagram of fin and tube array. Geometric specifications of heat exchange under study are given in this table. Two-out winglets are erected with attack angle of 60 degrees because such an orientation facilitates highest thermal augmentation. The aspect ratio of the winglet is kept equal to unit. Physical examination of the fin tube array shows that in its elevation, in its front view, the flow is periodic in the fin normal direction. So we have considered only one fin. Top view, the flow is also periodic in the cross stream direction. Further investigation shows that about the central plane. So we have adopted a periodic section in the fin normal direction and a symmetric section in the cross stream direction. So this helped us in restricting the computational expense. Now let me talk about the boundary conditions. Some of the boundary conditions are shown in this figure, and rest of the boundary conditions are tabulated here. Apart from this fin tube region, extended flow length equal to 10 times the fin space is provided at the upstream of the computational domain and 20 times the fin space is provided at the downstream of the computational domain. This allowed us to capture the entry and exit effects. Boundary conditions prescribed at the far field inlet is the uniform velocity and far field outlet is the outflow boundary. Now, after meshing the domain, we validated the model. So computational model is validated in reference to published experimental data over a wide range of Reynolds number. Characteristic dimension for defining Reynolds number equals twice the fin space, and reference velocity is the far field inlet velocity. Pressure loss is non-dimensionalized as a friction factor. Now, the objective of this study is to analyze the effect of streamverse translation of generators on the wake management. Generators are displaced in small steps in the streamverse direction while keeping the cross-stream position fixed. For an insightful study, two different cross-stream locations are selected. One is 0.3 and another is 0.7. So yellow region is the region in which the generators are going to be deployed, particularly in the tube downstream region. So I'm showing you a large view of this region. So here there are two cross-stream locations. One is 0.3 and another is 0.7. So the blue encircled is 0.3 and the red encircled is 0.7. So X by D is the dimensionless location in the streamverse direction and Z by D is the dimension location in the cross-stream. So let's have a look at the change in wake structure due to generator deployment. First, I'll talk about the baseline flow structures. Convection is mainly attributed to bulk motion resulting due to the prevailing flow structures. In baseline flow, all the tubes have recirculation regions in the downstream, as you can see in the figure. Such an occurrence is likely to make the affected fin area virtually ineffective for heat. But when the vortex generators are deployed, so I'm taking a sample location here. So the location is equals to X and Z equals to 0.6. And here I'm showing you the comparison of all three locations in the streamwise direction. So you can see that generator deployment has produced phenomenal changes in the flow structure at the same Reynolds number. Spread of baseline wakes reduces tremendously, which may be attributed to flow diversion caused by the generators. Evidently, the wake spread undergoes gradual growth with the streamwise shift in the generator. Further investigation of the wake structure is done by studying the velocity profiles. So I'm showing you the velocity profile as at the cross stream location 0.7. You can see that generators at all positions have caused visible shrinkage in the spread of the wake region, but the wake spread in the modified heat exchanger gradually increases with the streamverse shift in the. Now this change in the flow structure will translate in terms of heat transfer augmentation. So for that we are studying the effect on average heat transfer coefficient. First, let's talk about the heat transfer coefficient of each tube. So we have three tubes: leading tube, intermediate, and trailing tube. Now, attempt to curtail the effect of tube wakes may be understood as the tube wake management. As there is no wake present at the upstream of the leading tube, it undergoes little augmentation. Unlike leading tube, the two cross-stream generator positions have opposite effect on the downstream tubes. In case of generators positioned at Z equal to 0.7, the thermal augmentation is quite evident and it decreases almost linearly with the streamwise shift in generator position, but the change is small. In contrast, generators deployed at the closer cross-stream location, which is 0.3, are proving counterproductive for the downstream tubes, and the change is weakly dependent on their streamwise position. Now, apart from the tubes, thermal management of the wake region also involves heat transfer augmentation on the fin area affected by the baseline wakes. So the orange region here shows you the fin area, which is representative of the area affected by the baseline wakes. You can see that undisputed augmentation in the heat transfer coefficient is a clear indicative of successful wake management by the generators, but irrespective of cross-stream position, thermal augmentation decreases with the streamwise shift in the generators. Such a trend may be attributed to the increasing spread of wake regions with the streamwise shifting of generators. Highest thermal augmentation equals 238.7%, that corresponds to X and Z equal to 0.7. Now, all these 30.3% that corresponds to X and Z 0.3 equals 109.3%. Include resulted in significant reduction in the spread of the baseline wakes. Spread of wake region increases with the streamwise shift of generators. Combined effect of redirecting the approaching flow and the generation of longitudinal vortices produces appreciable thermal augmentation at the same Reynolds number. Streamwise shift of generators has a weak bearing on the overall augmentation. High percent at the Reynolds number of 4245, which corresponds to the winglet location X and Z equals to 0.7.
Okay, so I reckon there are no questions. So maybe a couple of questions from my side. So it was quite a comprehensive presentation showing the CFD studies which you have done. So first thing I wanted to ask, like, what was the basis of selection of the turbulence model to be K epsilon? So can you hear me? Yeah. Can you be a bit more louder so that I'm...
Yes, sir. So good morning, sir. Thanks for the question. You have a very valid question, and the answer to that question is there were a couple of criteria based on which we have taken this decision of using a two-equation model. This equation has some strengths and some weaknesses. First of all, because of this being a three-dimensional study of a commercial heat exchanger, so the computational domain is pretty large. So we could not afford to either conduct a DNS or LES study. So that's why we had to choose a model which is computationally sustainable for us.
Why K epsilon? Why
effects, curvature effects, streamline curvaturing? Because streamline curvaturing and flow separation is an inherent phenomena in these kind of flow domains.
Okay.
The weakness of this model is it is an added viscosity model. So it assumes the turbulence to be isotropic, which is not true in the real scenario.
Yes. That was my worry, or you can say query regarding this. Okay, but you have validated your results, right? That's what.
Yes, I have validated. Yes.
So that thing. Second thing, I was just regarding the boundary conditions. Like you mentioned that you have taken, I think, outflow boundary conditions at the external side when it is coming out of the system. So why
at the far downstream?
Far downstream. So why not pressure outlet boundary condition?
Because of flow reversal, because of possible.
So have you captured that flow reversal or flow reversibility at the?
No, we have not. We have not, because it is adequately mentioned in the literature that in the scenario where you anticipate vortex shedding, it is better to use far field boundary condition rather than boundary condition in the near vicinity because of associated issues, because these models are sometimes fail to capture these flow separation and flow reversal effects successfully. So that's why it is better to provide a ample downstream length so that all the gradients in the flow direction die out, and eventually the flow and the outflow boundary condition is able to justify the physics.
Yeah, okay. Because only worry was that like this outflow boundary condition, basically they are zero flux diffusion for all the flow variables which are associated with the flow. So, okay, so maybe you have done that homework before employing this boundary condition. Okay, I'm fine. Thank you for your answers, and appreciate the work which you are conducting. So I think once again we thank Dr. Amit for this presentation, and we can now request the next presenter to come and present. Thank you.
Hello all, my name is Harsh Arora. I recently completed my MTech from IIT Mandi. This research work I am presenting here is completed with the help of Mr. Ranjit Jha, who is a PhD scholar from IIT Mandi, and under the guidance of Dr. Pradeep Kumar, who is Assistant Professor, School of Engineering, IIT Mandi. We present a model named FoilNet, which is a convolutional-based neural network to predict pressure field across oscillating airfoils. This is a study which is based on the integration of computational fluid dynamics and machine learning. So as a subject of our study, we have used flow across airfoils. As we all know, computational fluid dynamics is used for simulating flow across airfoils. And the conventional process involves a lot of numerical experiments before coming up with new airfoil shapes. But there are some challenges and limitations associated with CFD. Especially for the large geometries, it takes a lot of computational resource. Also, sometimes it takes a lot of time, especially for large geometries and for transient simulations. It sometimes takes weeks or even months. Also, for a slight change in parameters, we need to set up a new simulation, which is a tedious task. So before discussing about how machine learning can be used to address these limitations of CFD, let us first discuss about what is machine learning. So machine learning involves algorithms which are based on data. They learn from the data. So we don't need to explicitly provide equations to solve something as we provide in the case of CFD. So in a CFD context, what we expect from a machine learning model is we will provide some data and the model will learn from the CFD data and later can be used to predict for the new scenarios. Deep learning is a subset of machine learning which uses neural networks. So as we can see here on the right side, we have a simple architecture of an artificial neural network, which is also called a multi-layer perceptron. This low-dimensional architecture takes input as a vector. As we can see here, in input layer we have 4 elements. So this is a linear vector of 4 elements. Further, we have some hidden layers. It computes over them, and later in the output layer we have 3 elements. So this will output a vector with 3 elements. But we have high dimensional architecture as well, which we will see later. So why using deep learning for CFDs? Primarily it is because it is very much time efficient. So compared to CFD simulation which takes days or weeks, here a deep learning model which is already trained can predict the physical quantity of interest in just seconds. Also the available CFD data can be used for training, and we don't need to set up numerical simulations again and again, which is a tedious task. Now here is another architecture from deep learning. This is called convolutional neural networks. These are mostly used for the high dimensional data such as images and videos. Now what a convolution operation does is it extracts different kinds of features from a given image. So as we can see here, there is an image of a face from in the input, and in the subsequent layers, these are called convolutional layers. These layers have different filters which extracts different kinds of features from a given image. So as we can see, first and second and third layer, all these layers are extracting different kind of features from a given image. So we will be using same kind of operations to extract different features from our input image, which is a image of a grid having airfoil, and then we will be later using that to predict the pressure contour. Now coming towards our problem case, we have used 14 different airfoil shapes to generate the training data for the deep learning model by performing CFD simulations across these airfoils at 18 different angle of attack in the range of 0 to 25. The Reynolds number is kept constant. So the objective here is first to develop a deep learning framework which can predict pressure contour across any given airfoil and angle of attack in the prescribed range. Secondly, to check how reliable is the deep learning model for predicting the CFD data. Third, to comment how we can use deep learning practices for the future aspects of CFD. So for our FoilNet model, the input is the image which will include grid and the airfoil shape, and the output is a pressure contour corresponding to the given input image. The architecture of FoilNet is based on a convolutional neural network based UNet encoder decoder. So as we can see here from the input image, this is just a convolutional neural network which is extracting different kind of features from the image, and we call it encoder here because it is encoding the information from high dimensional to a lower dimensional form. Now later after the encoder we can see here there's a decoder. So this is decoder is based on a convolutional transpose operation, and it is again converting the lower dimensional information to a high dimensional information, which is finally converts to a pressure contour, which is our output, target output. So what is UNIT here is because UNIT here is connecting different layers of the encoder and decoder. Why it is utilized here? Because different layers of encoder and decoder share common features at different levels. So UNIT is ensuring proper mapping and learning from all the layers of the encoder. So coming towards data generation part, we have used ANSYS Fluent for generating CFD data for all 14 different airfoil shapes at different angle of attacks in the range of 0 to 25. These were all the transient simulations such that with time steps, the angle of attack changes. So here in the leftmost, we have the images as obtained from the CFD data. But before feeding it to our model, we need to resize it and crop it. Also, we have gone for the augmentation. Augmentation is a technique which we use to increase the training data for better learning. We have 252 images in all from the CFD. We split it into training and testing. From the training images, which are 200, we gone for augmentation to increase it to 800 images for training purpose. The objective of training is to minimize the loss, the error between the image predicted by the foil model and the image we obtained from the CFD. So here is the expression for the MAE loss, which is defined over the predicted image and the target output image. Now to check how the model is learning, we keep an eye on the loss convergence. So here MA's loss is plotted with the epoch number. Here one epoch means when the model has seen all the data at once. So also from the images we can see after few epochs the model is able to recognize the airfoil, and later if we see it is able to recognize the contours even more fine. So after 100 epochs we have the loss value of 0.48. Now it means the model is learning. Now here is the MAE loss convergence from 100 to 300 epochs. So as we can see the loss value is decreasing, it means the model is learning. And we can see from 230 to 250 epochs there is a certain drop in the loss value. It means here the model is able to accurately predict the data. As we can see from the pictures, now the model is able to detect more fine features. Especially here we can see the green portion was not so fine in the second image, but in the third image it is able to detect it in the more fine picture. Further, if we see from 750 epochs to 1000 epochs, the average value of MAE loss is same. So we can say that the model is already converged, and that is the reason we have utilized the model after training it up to 750 epochs. So before analyzing how well our model performed, we need to first define some performance parameters. So first performance parameter here is defined on the basis of pixel-wise difference between the contour obtained from the deep learning model and the contour we have obtained from the CFD. So here as an example is a contour obtained after only 100 epochs of training, which is not well-trained model. And we can see the difference between this contour is plotted here as a pixel-wise error. The second performance parameter here is defined as the comparison of pressure profiles extracted from the pressure contours at different sections of the airfoil. So here we can see the blue one is the CFD and the dotted red one is the model prediction for the same example as we shown in the last slide. And we can see there's a lot of deviation because the model is untrained after 100 epochs. Now we utilize those performance parameters to check whether how well our model is performing on training data. So from the training data, we have randomly selected 3 different airfoils and we have plotted the results here. As we can see here in the first airfoil, prediction and target output contours are pretty similar. And from the error profile, we can see there is only a small difference at the edges where there is a sharp change between the contour bands. Also from the performance parameter 2, we can say that at these different sections of airfoils, the approximation is quite close and there is no as such deviation in the pressure profile. From the second airfoil we choose from the training data, the scenario is pretty much similar. And also for this airfoil, it is quite similar. Coming to our testing data, again we have also selected 3 different airfoils from the testing data in the pressure profile as expected at different sections of airfoil. In the second airfoil we got from the testing data, again the scenario is pretty much similar, and we have more error in the bands where the contours are changing sharply. Training case, so it is performing better as compared to the other testing airfoils. So to summarize, we can say the model was able to perform accurate on the instances from training data. Only the error was in the vicinity where there is a sharp change in contour, and the error was less than 1%. However, if we talk about the instances from testing data, the error was quite amplified, and it was mostly under 2%, but in few pixels it was up to 12% also. But with further improvement in the model, this error can be reduced and accurate predictions can be ensured in future. So to conclude, we can say as per the objective of our study, we successfully delivered such a model to predict pressure contour across airfoils and in different angle of attack. Also, we defined 2 suitable performance parameters for evaluation of our model. And also we analyzed that this was a very fast prediction as compared to CFD practices. With further improvement in this such kind of models, we can use it reliably for the future aspects of CFD. Thanks.
Thank you, Mr. Harsh.
Please.
I think it was Mr. Harsh, right?
Yes, sir.
I just saw some other name. Yeah. So thank you for the presentation. And yeah, we all are moving towards that era where deep learning is becoming an integral part of any study, irrespective of the area in which we are venturing as R&D component for as such. So just a couple of questions I have from my side. Before that, I would request anyone from the guest list, can you please raise your hand so that we can ask to the presenter? Yes. Yeah. I think so one hand is there.
Yeah. First, good presentation. However, I was wondering because you have used deep learning, which is good, demonstrated its capability, but I was wondering whether, although you mentioned in your conclusion, but whether you demonstrated its effectiveness is what I am wondering. You said that very fast computations was done, but do you have any results or data to demonstrate that the pressure that you obtained from the deep learning technique as compared to the traditional CFD technique, whether there is a comparison in computational time?
I have not done that analysis quantitatively, but I mean, once we train the model, so it just take it's an instant thing. I mean, if you want to predict something, it just takes seconds to get the results. But yeah, of course, training time, if we include, so it takes some time to train.
Yeah, so you have to include all those times, and if you can show quantitatively the effectiveness, that will make your work much more valuable and impactful. Fine, thanks.
Sure, thanks.
Thank you for your question and then the input to the presenter. So yeah, a couple of questions from my side. So what sort of activation function you used? Have you used any activation function?
Yes, sir. I have used railway activation functions in the mostly in all the layers, hidden layers, and in the last layer I have used sigmoid.
Okay, so last one you have used sigmoid. And then one more thing I wanted to ask, like you used CNN, right? Convolution.
Yes, sir. CNN based. It's an encoder decoder. Yes.
Yeah. So means, do you think it is good enough to go, or we should use the traditional ANN type of?
So for high dimensional architecture, we need such models. So I mean, if we use ANN, we need to convert the data in some other form, or maybe have to go for reduced order modeling. That is again, if we use that, so there are chances uh, that will have more errors because we are using 2-3 conversion techniques.
Okay, okay. And then the last one was regarding the augmentation, which I am bit conservative because means you are increasing the data point, right, by using this augmentation. So do you think it is safe enough, or the results we are having?
Augmentation includes flip. Sometimes it flips the image, sometimes it crop and zoom the image, and it also rotates the image. So we need to take care of that. So in my case, when I did augmentation, I excluded the rotating part. So because if I include that, it will come up with errors because I'm already performing a study on angle of attacks. So it can fake that.
Okay. And the last one, like, can we couple this thing with couple of transfer and the loss which is happening through them means not required. So can we couple GA with your neural network means technique to come up with something more robust?
I don't have much idea about how we can couple GA, but I can surely tell we can include parameters.
Okay, but yeah, regarding the GA thing with
I don't have much idea about the GA actually.
Oh, no, that's fine. Thank you. So thank you, Mr. Harsh, and I think we will now go to the next presentation. Best of luck. Yeah, best of luck for your endeavors. Now we will go to the next presentation, please.
Beniwal from IIT Roper presenting the paper presentation on the topic humidification, dehumidification, desalination, study of a PET humidifier. Figure shows global physical and economical water scarcity. According to World Water Development Report, around 1.2 billion people across the world live in the areas of physical water shortage, and nearly 1.6 billion people face economic water shortage where they lack necessary infrastructure to take water from rivers and aquifers. And by 2025, nearly 2 billion people will be facing water scarcity. So why HDH desalination? As rural and small communities have low water demand of the order of 10 to 100 meter cubes per day, whereas conventional desalination plants produces water of the order of 100,000 meter cube per day. Therefore, for decentralized water production, desalination by dehumidification technique serves our purpose. Also, HDH has low maintenance, so it can be operated by a medium skilled person, and also it has low operating cost. This slide shows schematic of humidifier and the psychometric chart. As can be seen from the figure 1, it is the schematic of the humidifier. The humidifier consists of 3 sections. The top section, that is the spray zone, where the heated water is sprayed through the nozzle. The middle section is known as packed bed zone. It consists of closely packed bed of acrylonitrile, butadiene, styrene, that is ABS material with 1 mm thickness. Here the air gets heated and humidified. The third zone, that bottom zone, known as supply air zone. Here air is supplied in the humidifier. So the process occurring in the humidifier can be understood with the psychometric chart. Let the air is supplied in the humidifier at condition A. So after passing through the packed bed zone, the air gets heated and humidified and it achieves the condition B. So the amount of moisture that is carried by the air at point B is omega B, that is humidity ratio, and at point A is omega A. So the total moisture carried will be the difference of omega B and omega A. Figure 3 shows the schematic diagram of the humidifier system. So where water flows from the brine tank through feed pump, passing through the water rotameter and getting heated to the required temperature through the heater to the inlet of the humidifier. On the other hand, air is supplied through blower to the humidifier after passing through the air rotameter. The heated air is passed from the top of the humidifier. This heated air is then passed to the dehumidifier section where it gets condensed as distillate or fresh water. The next slide is modeling of the humidifier. So the main important parameter for the design of humidifier is its effectiveness, which is defined as the actual change in the enthalpy to the maximum possible change in the enthalpy. So the effectiveness would be calculated from the point whether air or water is having the minimum change in the enthalpy. So according to that, we have two cases. The case 1 where del H maximum for air is less than that of the water, and in the case 2 where del H maximum for the water is less than that of the del H max of air. So according to that, the mass flow rate of the brine can be calculated as the mass flow rate of inlet of water to the humidifier minus this component, and this component is known as mass flow rate of evaporation. So from that we can calculate the fresh water produced, that is liters per day, from the mass flow rate of the evaporation. Now we come to the resultant discussion section. So the numerical study of the humidifier was performed and the equations were solved using MATLAB, and the results are presented here. Figure 4 shows effect of inlet water temperature on the fresh water production rate for a specific temperature of inlet air. As the temperature of inlet water increases for a given temperature of inlet air, the fresh water production rate is also increased, as the moisture carrying capacity of air would be increased. Now figure 5 shows that more the air is unsaturated at a given temperature of air, higher will be its moisture carrying capacity, and eventually higher fresh water production rate would be obtained. Figure 6 and 7 shows the calibration results of the measurement instrument of the humidifier system. Figure 6 shows the mean mass flow rate of air measured in both cases, that is ascending and descending, is quite similar, and there is linear relationship between the reference mass flow ratio, which is measured by rotameter, and mean mass flow rate of air measured via anemometer. Similarly, in figure 7 shows a linear relationship between the reference flow, that is through rotameter, and the actual flow measured with the help of the volumetric measurement and the stopwatch. So here we comes with the conclusion of the presentation. So a humidifier is a simple in structure and also it is easy to operate. As the temperature of water in the humidifier increases, the mass flow rate of evaporation also increases, and at lower temperature of inlet water to the humidifier, the relative humidity of the inlet air plays a substantial role in the freshwater production. The calibration ascertains the actual performance of the humidifier system. The authors wish to acknowledge the support provided by Science and Engineering Research Board, New Delhi, India, and the Department of Mechanical Engineering at Indian Institute of Technology, Ropar. The following are the references which are used while making the presentation.
Thank you, Mr. Ravi, for such a nice presentation. And in fact, we are going to that age or that era when we will be having a lot of scarcity of water, and energy and water, they go hand in hand. So this is a very relevant study in today's era. So that makes a lot of impact. So now I would request from the guest list, anyone is having any query, please raise your hand so that we can ask. Yes. So I think no one is having. So maybe a couple of questions from my side. So I understand this results which you have shown, they are quite preliminary results, right? Because not much of I have not seen any heat transfer parameters which were being given in this presentation. So am I right, or is this what?
Yes, sir. These are preliminary results only at the start.
Okay.
That's the basic calibrations and
that's what I felt. So what all plannings you have for this entire work which SCRB is sponsoring? If you know some things, you can put some light on that area.
So the main here is to integrate the humidification and dehumidification system, to integrate it and drive with the help of solar energy. And for solar energy, we will be using direct adsorption, means DASC system, direct adsorption solar collector system, and in that it would be driven with the help of a nanofluid lens system. It would be there. So it's two part.
So when you are saying that you are planning to use solar energy, so I understand you will be having some sort of arrangement for storage also, energy storage, to make it perennial, or not planned for that?
At present, it's not planned, but as it goes further, that's an important aspect we have to consider, because solar is not available 24/7 or throughout.
That's right, to capture the diurnal variation and then utilize it efficiently. So I think that can be one aspect which should be included. So I think yeah, these are very preliminary studies, and the results were quite evident. So as such, I don't have any more query, and I wish you all the best for your endeavors with this project. And I'm pretty sure means water is one of the most important constituent of our life. So yeah, this will, and when you are saying that you are coupling it with solar energy, so that concept of water energy nexus, if what we can say, that is also coming into picture. So this is a very well planned project which you are working on. I wish you all the best for your endeavors.
Thank you, sir, for your encouragement. Thank you so much.
So now I request the next presenter to
this section. In Indira Gandhi Center for Atomic Research, Kalpakam, I'm going to present the work on analysis of sodium fuel phase scenarios in mutually connected cells by developing suitable models. Introduction. Liquid sodium is having many advantageous properties as coolant of phosphate reactor. Main disadvantage is its high chemical reactivity with oxygen. Even in low oxygen concentrations, it reacts with oxygen. Under accidental leak conditions, liquid sodium can be exposed to air, and its rapid exothermic oxidation reactions with oxygen can continue as sodium fire. The main modes of sodium fire are full fire and spray fire. So in this work, we are going to analyze full fire. In full fire, sodium burns with very small flames, and the flame is very near to the full surface. And the major combustion products are sodium monoxide and peroxide. And these two reactions will show their formation. And the amount of energy will be around 10,000 kilojoules per kg of Na. And these two reactions will decide the stoichiometric ratio of the combustion process. And another feature of sodium full fire is aerosol generation. And generally 30% of the sodium burn can be released as peroxide, and 70% of sodium burn can be formed as the monoxide.
Cutting the
Sodium
text.
fire is a safety concern because of combustion heat release and aerosol generation and concrete interactions. If it comes in contact with concrete, it will interact with the concrete. So analysis of fortunated sodium fire events for estimation of their consequences is required for the effective implementation of various protective measures from the reactor design stage itself, and it is an essential part of the safety procedure implemented. The typical sodium full fire is shown here. Sodium full fire in connected cells. Generally, SFR buildings are divided into compartments and they are interconnected with openings. And the schematic of the two-cell configuration considered is shown here. And there is a basic two-cell configuration. And cell 1 will be having sodium full fire, and it is connected with cell 2 by opening of height h. And cell 2 is connected to the exhaust system. The modeling details of sodium fire cell 1 are shown here. And gas will be considered as a single node, and sodium pool, floor, and wall will be considered as node system. And oxygen mass transfer from gas to pool surface will be considered based on the mass transfer coefficient, and this mass transfer coefficient will be estimated using the heat transfer analogy based correlations. And the energy generation rate will be estimated based on the burning rate of sodium estimated and using heat of combustion. And other processes considered here are from sodium pool surface to gas convection, and sodium pool surface to gas radiation, and gas to wall convection, and sodium pool surface to wall radiation, and conduction through the pool to the floor. The model considers the cell geometrical parameters, material properties, initial conditions, and pool surface area. Based on the heat transfer process considered and mass transfer process considered, a set of transient equations will be framed for a gas heat balance, gas mass balance, cell wall heat balance, and floor wall heat balance. By solving these equations, the transient gas temperature, pressure, wall nodes temperatures, floor nodes temperatures, oxygen concentration, and sodium burning rate will be estimated. The mass flow rate between the cells can be estimated based on the local velocity variation along the opening height. And when these two cells gas temperatures are different, the neutral plane will vary from its mid of its height, and that variation can be estimated based on these cell temperatures. And based on these cell temperatures and displacement of the neutral level, we can get the mass flow rate between the cells. And coming to cell 1, based on the process occurring, the mass and oxygen conservation along with energy balance is applied for the gas by considering sodium wall and floor of the cell. And mass and energy transport between two cells due to gas flow is evaluated using the constitutive relation for pressure in the interconnected cells. And for cell 2, mass and oxygen conservation along with energy balance is applied for the cell gas by considering wall floor and its ventilated conditions. The two-cell full fire model developed is used to simulate the JAES experiment, which was conducted in Sulfa facility. In this experiment, 2.25 meter square pool was created at the center of the floor in cell 1. 55 kg of sodium was drained in 2 minutes. Cell 1 volume is 33 meter cube, cell 2 volume is 38 meter cube, and the area of opening between these two cells is 1 meter square, and the height of the opening is 0.2 meters. Initial conditions of the cells are 19 degrees centigrade and 21% oxygen concentration, and duration of this experiment was 50 minutes, and it was conducted under ventilated conditions. Cell 2 vent duct is connected to the exhaust system, and the reference pressure and flow rate values of the facility are used to evaluate the mass flow rate from the cell 2 to exhaust system. And the thermal hydraulic interactions between these two cells through this opening will decide the two cell sodium fuel fire characteristics. Those things are evaluated in this study. Cell gas temperature is an important parameter. It describes the inside thermal conditions, and the average gas temperatures predicted by the model are in line with experimental results in both the cells. And in experiment, 2 minutes dumping time is there, but in simulation, at time t is equal to 0 itself, the fuel is available like that we have assumed. That can be the reason for the initial higher gas temperature predictions. And the main thing is, under 1 meter square opening, at the end of the experiment, there is a big difference between these two cell temperatures. The variation of wall surface temperatures in the two cells is shown in this figure. The wall temperatures predicted are in fairly good agreement with the test results for both the cells. These results confirm the prediction capability of mass flow rate methodology used and the heat transfer models used. This figure shows the variation of oxygen concentration in the two cells. Model predictions for oxygen concentration variation trends are similar with small concentration difference between the two cells like observed in experimental results. Uncertainties in the measurement and the constant stoichiometric ratio used in the model and further conversion of the products at later time are reasons for the difference between the experimental and numerical results. This figure shows the variation of sodium catchment temperature, and the trends predicted are fairly good, and the maximum temperature predicted is in line with typical sodium temperature that has been observed in experiments. This figure shows the variation of mass flow rate through the opening. This data is not available from the experiment. The same experiment was used to validate the Spinix code. Hence, the present model results are compared with Spinix code results. The present model predictions are in line with Spinix code predictions. Base case of 1 meter square opening area has been analyzed for different heights of opening by taking the opening area constant, and by increasing the height of opening, good mixing of gases occurred due to increased mass flow rates between the two cells. This can be seen by the gas temperatures in the two cells at the end of the run. The base case has been analyzed for different areas of opening from 1 to 6 meters square, and the height of the opening is taken as 1.62 meters. For 6 meters square opening area, the cell gas temperatures in two cells are very nearer to each other, and the variation of cell gas temperatures and oxygen concentrations are shown in the following figures. The oxygen concentration values in both the cells are almost same, and their variation also very similar. And this variation shows with 6 meter square opening, the two cell model predictions are approaching towards the single cell model. The base case of 1 meter square opening has been analyzed for different CD values. The influence of discharge coefficient on the overall thermal consequences is minimal for the range of discharge coefficient values considered. Conclusions. Two cell configuration sodium fuel fire is analyzed by modifying the zone-based fuel fire analysis code. Model has been validated with JEA benchmark experimental results. Code predicted trends for the transients of cell gas, wall temperatures, and oxygen mole fractions are in line with the experimental results. Predictions confirm the models incorporated for fluid flow and heat transfer in mass energy balance along with constitutive relation for the interconnected cells are fairly representing the process occurring during the two cell fire. Parametric studies have been carried out for different heights of 1 meter square opening and various sizes of openings, and the results revealed the interconnected cell full fire characteristics and confirm the capability of the model. The present study also confirms the benchmark 2-cell full fire case, and the results are useful in the detailed analysis of the scenario by using field modeling. The validated tool is useful in the sodium fire safety analysis of SFR.
Thank you, Mr. Nagarjun Rao. So
yes, sir.
Now I request, I think Mr. Shiva K. Batina, he is raising his hand. So yeah, Mr. Shiva, please go ahead.
Thank you, sir. It's a good presentation. I have two doubts regarding this. Please correct me if I'm wrong. How did you do the lumped body analysis for the gas?
Lumped mass, the gas will be considered at one temperature because in cell 1, the turbulence will be very effective and it will be mixed very fastly. So we can use this lumped model for getting the average temperature, particularly for estimating the what is the pressure rise, particularly in enclosed cells.
Yeah, but in your temperature curve, it is showing enough time to reach the steady state. According to my knowledge, lumped body analysis, it should be constant temperature throughout the cell. But it is showing sufficient time to reach the cell for a constant temperature. Still, I am not able to see that steady state trend.
Yes, because this is under ventilated condition. The cell 2 is connected with exhaust system, and once the pressure in the cell 2 is more than atmospheric pressure, the gas will be going out based on the system characteristics of that exhaust system. So because of that reason, this experiment was conducted up to 50 minutes. So they continued only for 50 minutes. Still sodium is there.
Okay, sir. Have you done any Biot number calculations? On what basis are you telling this is lumped body?
Lumped code for gas, it is just to get the average completely mixed means what is the temperature we can get it. This approach is used for full fires in enclosed system. It is something like one zone model. It is one zone model, and these one zone models will be useful for getting the system characteristics. And if you want to know its characteristics, particularly under different conditions, you can use these tools for estimating the conditions for n number of cells which are there in reactor buildings. That is the main purpose of this work.
And are there no convection radiation within the gas? You're telling only conduction.
No. We have taken radiation, and the process from sodium pool to gas, we have considered the radiation as well as convection, and from sodium pool surface to the wall, radiation also we have considered. And one cell to other cell radiation we have not considered. Only convection we have considered.
Okay, one more thing. You have mentioned that you don't have mass burning data, but all these temperatures depends on mass burning data only, na?
Mass burning data is available. Mass burning data they have given.
Experimental data is not available, you said.
No, that is for flow rate. That is for flow rate. They have not given. The in between through this opening, what is the flow rate variation during this process that they have not measured.
And for 1 meter
in their experimental result, but one more person has validated this experiment with their code, Spinix code, and he has given that the flow rate between the two cell 2 to cell 1 means the non-burning.
I'm not asking from the code. I'm asking from experimental data.
Yeah. From experimental data, they have measured temperatures, but the flow rate I didn't get in their whatever paper.
That's what my point is. That's what only based on the mass flow rate only the temperatures you can achieve.
Yes.
Without knowing the mass burning rate, how accurate these temperatures?
Mass burning rate we know. How much oxygen is going to the surface. That based on that we can get it. That they got it around 15 kgs per meter square per hour. We got around 14 kgs per meter square hour.
Okay. Then that will be the mass burning rate, na? If you divided it with the area.
That is a
kg
mass
per meter square second. Kg
per meter square per hour. That is
that is mass burning rate.
Yes, mass burning rate of sodium that will be estimated based on the mass transfer of oxygen to the pool surface. That is the main thing which will decide the energy release
And
I think you both can have a discussion offline because I can understand lot of good information are being exchanged between both of you. So, but with the constraint of time, so I would request, of course, the means the questions were quite sensible and that makes lot of sense. Had one query, so
facility, Sapphire facility they will call, sir. It is there in Japan. And this one, whatever two cells they have separated, that is actually single cell. And because of this experiment sake, they have separated like this. And above these two cells, one more cell is there actually. Through that, the ventilation system connect.
I'm just trying to imagine the
mail ID.
I think it will be. You can put it on the chat box, so you know how to open the chat box. Okay, for chat given to Mr. Siva K. Bathina.
Sir, my mail ID is pmr@igcar.gov.in.
Okay.
It is there in our that document, whatever abstract documents it is there.
Okay, thank you, Mr. Chuna, for the email address.
Thank you, sir. Thank you very much for adding this one. Yes.
Thank you. So now I request the next presenter to share their slides.
Hello everyone, I am Nitesh Kumar. Today I am going to present my research work titled Computational Analysis of Thermal Hydraulics of Supercritical Carbon Dioxide in Horizontal Finned Square Microchannel Heat Sink. So this is the outline of my slide. First I shall give a brief discussion about supercritical fluids and its peculiar properties, then the motivation behind my present work, then some relevant literature studies. After that I shall explain my computational domain and impose boundary conditions, and then grid independent study and model validation, and then last result and conclusion. So now coming to the introduction, here I shall briefly explain about supercritical fluids. So first, what is the supercritical fluids? So when a fluid is heated beyond its critical pressure and temperature, it transforms into supercritical fluid. As it can be seen from the figure, that as the temperature increases, the meniscus between liquid and gas disappears and the states merge to form supercritical fluid. Above the critical temperature, there is no phase distinction occurs no matter how much pressure is increased. Supercritical fluids have properties of both gas and liquid. It means that when kept in a container, it expands like gas and has density like liquid. When heat flux is applied to the walls of a container filled with supercritical fluid, a hot boundary layer forms which compresses the fluid in the form of pressure waves. This process is known as piston effect and has been identified as fourth mode of heat transfer besides conduction, convection and radiation. Here I have shown the variation of a specific heat and density of supercritical carbon dioxide. So for a given pressure, a specific heat increases, reaches to the maximum and then decreases. So the point at which the specific heat is maximum is known as the pseudocritical point, and the maximum property variation of supercritical fluids takes place near the pseudocritical point. Now coming to the motivation behind my present work. So what is the main attraction of carbon dioxide? So the main attraction of carbon dioxide is its lower realizable critical pressure and critical temperature compared to other supercritical working fluids. Also, if we compare with the conventional system where supercritical fluids are not being used, the compressor size reduces dramatically because of having high working pressure. This is because required compressor volume is roughly inversely proportional to the suction pressure. Here I have shown some of the applications of the supercritical carbon dioxide. That includes cooling of critical component of space shuttle, cooling of electronic component under microgravity condition, and nuclear reactors using the carbon dioxide as in indirect cycle. So apart from heat transfer point of views, carbon dioxide has got some applications in chemical research area also, like nanoparticle synthesis inside near critical carbon dioxide. Here I have shown the most relevant literature related to supercritical fluids as heat sink coolant. So of all the found literature, it has been suggested that supercritical carbon dioxide can be used as a heat sink coolant with improved heat transfer coefficient. Moreover, most studies have been done for macro channels. Therefore, an attempt has been made in the present study to abridge these particular voids through quantification of the heat transfer characteristic of supercritical carbon dioxide in a horizontal micro heat sink with microfilm subjected to heating condition. So this is my computational domain. In the present simulation, micro channel of hydraulic diameter 0.5 mm and length 10 mm is chosen. Mass flux at the inlet, pressure outlet at the outlet, uniform heat flux at the side walls are employed. The simulation parameters and their range is shown in the present table. In the present simulation, heat flux varies from 20 to 100 kW per meter square. Mass flux varies from 100 to 1000 kg per meter square second. Operating pressure in the present simulation is 8 megapascal and inlet temperature is 305 Kelvin. So in the present simulation, SST K omega turbulence model is used, and the requirement for SST K omega model is to keep Y plus value less than 1. So to ensure Y plus value to be less than 1, inflation technique is used with first layer thickness of 0.0002 mm. And the corresponding values of bulk temperature and pressure drop for different grid sizes is shown in this table. Relative error for bulk temperature and pressure drop is calculated, and it is observed that grid 3 yields less than 0.07% and 1% change in bulk temperature and pressure drop respectively. Therefore, grid 3 is chosen for the further calculations. For validation, there is a scarcity of available experimental data for carbon dioxide's flow in square macro channels. Therefore, available correlation is used to validate the present model. And this figure shows the comparison of present simulation data with the available correlation. An excellent agreement can be observed with the correlation proposed by Wang et al. And a reasonably good agreement can be observed with the Y et al. And Mokri et al. Correlation data. Now coming to the result here. First, I have shown the effect of presence of microfilms on the heat transfer coefficient. The comparison of heat transfer coefficient with and without baffle is shown in this figure for two different heat flux values. It is evident from the figure that heat transfer coefficient with a single pair of baffle is significantly higher as compared to heat sink without baffle. Also in plain microchannel, heat transfer coefficient decreases monotonically along the channel length, whereas heat transfer coefficient with a single pair of microfilms is greatly improved in the degraded region and resulted in the lower wall temperature as compared to heat sink without microfilms. This is due to flow interruption caused by the presence of microfilms and increased surface area. Moreover, heat transfer coefficient is higher both in the region where microfilms is present and in the downstream region where there is no microfilms. In this figure, I have shown the effect of mass flux on heat transfer behavior. Higher heat flux leads to elevated heat transfer coefficient regardless of the power level. This is because larger flow rate yields greater Reynolds number, consequence of which is a rise in turbulent intensity. This leads to augmented turbulence mixing, which is characterized by velocity fluctuations and more randomized cross motion, eventually leading to greater wall to fluid interaction and hence amplified heat transfer coefficient. Flow and thermal characteristic of in microchannel heat sink is shown in velocity and temperature contours. So in case of plain microchannel, maximum velocity is near the core region, whereas in finned microchannel heat sink, the velocity profile is disrupted and maximum velocity zone is shifted in the opposite direction of the microfilms and towards the wall. So temperature contour is shown here. From the contour, one concluded that wall temperature along the entire microchannel length in plain microchannel is significantly higher compared to finned microchannel. Which is detrimental to the performance of heat sink. Moreover, due to the presence of microfilms in microchannel heat sink, development of thermal boundary layer is interrupted and it enables more efficient turbulent diffusion of energy, which leads to gradual temperature change. Similar to the velocity profile, the maximum temperature in the plane microchannel is in the core region. Whereas in fin microchannel, the region between the microfins is signified by the presence of low temperature region. The higher temperature zone is shifted towards the lower half portion of the channel surface. Here, in order to optimize the number of baffles, simulation have been performed for 1, 2, 3 and 4 pair of microfins. So this figure shows the effect of number of microfins on heat transfer coefficient. It is evident from the figure that average heat transfer coefficient increases significantly with number of microfins. For the plane microchannel, the heat transfer coefficient is lowest, and with increasing in number of microfins, heat transfer coefficient increases significantly. Also, in finned microchannel, heat transfer coefficient decreases sharply in the no baffle region due to the deterioration in heat transfer, especially at this location, which is axial location at z is equal to 5 mm. And this is primarily due to the flow obstruction and sudden change in flow structure caused by the presence of microfins. And the comparison of pressure drop is shown in this table for different pair of baffles. Pressure drops increases significantly with baffle number owing to the flow resistance produced by microfins. From the comparison of heat transfer coefficient and pressure drop, 3 pair of microfins provide similar level of heat transfer coefficient with significantly lower pressure drop as compared to the 4 pair of baffles. So in the present study, an attempt is made to study and analyze the thermohydraulics of supercritical carbon dioxide inside microchannel heat sink with microfins. So it has been concluded that heat transfer performance of microchannel heat sink with and without microfins is compared, and heat sink with microfins show superior heat transfer performance. So comparison of heat transfer performance for different pair of microfins is done, and optimum pair of microfins is identified. And increasing pair of microfins from 3 to 4 doesn't provide much better heat transfer performance but poor hydraulic performance. Also, with increasing heat flux, heat transfer coefficient increases, and also as the mass flux increases, it yields to higher Reynolds number, which further increases turbulence intensity, and eventually it increases heat transfer coefficient. This is the reference. Thank you.
Thank you, Mr. Nitesh, for the presentation. So, of course, supercritical CO2 is that fluid which finds its suitability in any area. You mean like go to solar thermal high temperature for power gen, and even you come to some lower temperature refrigeration. So each and every place you can find the applicability of supercritical CO2. And of course, this is a very good study, like a relevant study, where microchannels with fluid as CO2 has been studied. So I think now I will request the guests over here to raise their hand if they have any questions. Yes, okay, so no question. So maybe one question from my side. So I can see that there are a couple of modulations, like undulations, means peak and down for the baffled system when we are seeing both the heat transfer and the temperature. So was it quite periodic throughout? Have you given a thought about it, why it was increasing, decreasing, again increasing? Is there any pattern which is being followed? At what pattern it is followed? Have you studied that, or not part of your analysis?
Sir, actually we haven't done any study on the periodicity, but actually that periodicity was not more prominent. In fact,
okay. Yeah, please go ahead.
Sir, actually this periodicity was more prominent for the one pair of baffle, but as we have increased the number of pairs, like for 2, 3 and 4, so its periodicity decreases. And this periodicity, I think, is mainly because of the sudden change in the flow structure. Suppose like we have a pair of baffles near the inlet, and as we go downstream, a pair of baffles are absent. So there is a sudden change in the flow structure. So that increase and decrease is mainly because of the sudden change in flow structure.
Okay. And yeah, one more question I'm adding, sorry. And have you got any optimum fin height when you are
Yes, sir.
including those protrusions? Yeah, please.
Sir. Actually, sir, we have done simulation for varying width, height, varying fin height, varying fin width. In fact, actually, we haven't included that result in this
Okay. So
presentation,
you have
but
done
we have
that
done.
study.
Yes,
Okay.
sir. Yes, sir.
Thank you, Mr. Nitesh. So once again, thanks to all the presenters and the guests who are means there throughout this session, and I thank the organizers of FMFP 2020. So to give this opportunity to me to share this session. So if there are no further queries, so I think we can close the session.
Okay. We thank Professor Dibakar Rakshit for chairing the session. From 1:30, we will have a keynote lecture. In Hall 3, we will have Professor Ganesh Natarajan. In Hall 4, there will be Professor Ashish Kumar Sen. And next presentation session will begin from 2 p.m. We again thank you, Professor.
Thank you.
Okay.
Organizer.
Thank you.
Okay.
yeux est trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites.
Live session, sir. Yeah. Okay, so the speaker for this keynote session is Dr. Ashish Kumar Sen, and it is my pleasure to introduce him. And
hello, good afternoon. I welcome you all. I welcome Professor Ganesh Natarajan, the speaker, and Professor Somnath Rai, who will who will chair the session. So, Professor Rai, you see, Professor Natarajan has joined.
Professor Natarajan, no, I cannot see him.
Professor Rai.
Yeah, yes, I cannot see Professor Natarajan. So
okay, maybe
you should wait few minutes for him.
Yes, yes. So, Professor Rai, Somnath Rai.
Yes.
So he's having some internet issue. He's coming online.
Okay. So let's wait another few minutes.
Yes.
I can see Ganesh has joined. Professor Natarajan has joined.
Professor Natarajan.
Hello.
Yes.
Am I audible?
Yes, yes, you are audible.
Yeah. Good afternoon, Somnath.
Good afternoon. Good afternoon, Ganesh.
Yeah.
So should we start?
Yeah, I'll just share my screen too.
Yeah. This is a keynote lecture from Professor Ganesh Natarajan. The title of the talk is Towards a Unified Framework for Gradient Schemes in Unstructured Finite Volume Solvers. Professor Natarajan is currently an associate professor at Department of Mechanical Engineering, IIT Palakkad. He completed his BTech in Mechanical Engineering from NIT Calicut, and for his ME and PhD was from Aerospace Engineering Department, ISC Bangalore. After working as a year as a postdoctoral fellow in University of Minnesota, he joined Department of Mechanical Engineering at IIT Guwahati, and there he had an 8-year-long association. After that, he moved to IIT Palakkad in December 2018. His primary research interests are in development of numerical algorithms for compressible and incompressible flows with a focus on inverse boundary methods and unstructured finite volume techniques. So I welcome Professor Natarajan to present his keynote lecture on unstructured finite volume solvers with a focus on gradient schemes.
Yeah, thank you, Dr. Somnath. Is my screen visible?
It was visible earlier, but now I can see blank screen.
Yeah, just a moment.
Yes, it is visible now.
Okay, so some connectivity issue. Please hold on. Yeah, I think, is this fine now?
This is fine now. This is fine now. Only somehow I am spotlighted, so let me turn off my.
Okay, so yeah. I hope I'm audible and the screen is clear and visible.
Yes. Yes.
Yeah.
Please go ahead.
Yeah. So good afternoon, everyone, and thank you, Dr. Somnath, for the kind words of introduction. Let me start by thanking the organizers of FMFP 2020 for providing me this opportunity to present some of our research efforts towards a unified framework for gradient schemes in unstructured finite volume solvers. And
Okay, yes.
Has it gone to the second slide?
No, it's the first slide only.
There seems to be some issue at my end.
So, Professor Natarajan.
Yes.
You can share in your desktop, then if you can view, then maybe it will work.
Right.
Actually, I've shared my desktop.
Okay, but it is not going to the next slide.
Yeah, just a moment. Yeah, I think it's clear.
Yeah. Yes.
Okay, thank you. Okay, so as we all know, unstructured finite volume solvers are widely used in numerical simulations, both in industry and academia, for solving problems involving complex geometries. Most industry standard codes today employ second-order accurate collocated finite volume solvers as their primary workhorse. As such, in such a framework, it's necessary that we compute the gradients because they are required both for diffusive fluxes, such as the viscous stresses and the heat fluxes, as well as the convective fluxes if you need second-order accuracy. Clearly, when you post-process the data, you're looking at ideas like skin friction distribution and stagnation heat flux, and you need to compute quantities like aerodynamic drag and total heat load. And all of this clearly depend on the accuracy of the gradients. the gradient accuracy reflects in the not accuracy of the computed solution, and this is a major challenge, particularly on skewed and distorted meshes. So CFD practitioners would know that there are two popular families of gradient reconstructions, namely the least squares and the green-gauze approaches. So just before we get into the gradient reconstruction and the unified view of these schemes, a quick look at the nomenclature for unstructured finite volume solvers. As you can see on the left, you have a cross-section of an unstructured mesh. You have the cell I and its immediate primary neighbors, which are hatched in red color. And of course, you also have other neighbors in its vicinity, such as the node sharing neighbors, J2 and J3. Most of unstructured meshes are typically non-orthogonal and skewed. And what does this mean? The panel on the right shows that if you have the line joining the cell centers I and J, and it's not parallel to the unit normal vector to the face F shared by these cells, it's a non-orthogonal mesh. And if the line joining I and J does not pass through the face center, you have a skewed mesh as well. So essentially the fact that most unstructured meshes could be non-orthogonal, skewed, and in particular you could also have curvature, stretching, and high aspect ratios is essentially a challenge for not only the unstructured solvers but also the gradient schemes. A quick look at the two common families of gradient reconstructions, which are the least squares reconstruction and the green-gauze reconstruction. The least squares reconstruction is based on a least squares minimization principle, and the idea here is that you try to write down or estimate the value at the neighbor, phi j estimated, using the values at the cell I and the gradients at the cell I. And if you are using a truncated Taylor series and you throw out terms of order h square and higher, you have a linear, it leads you to a linear least squares approach. The idea here being you write down such an equation for each of the neighbors involved, and then you have as many equations as the number of neighbors, but you have only two unknowns here or three unknowns depending upon whether it's a 2D or a 3D domain. And the gradient vector is a 2x1 or a 3x1 column vector. And the idea therefore is that because you have an overdetermined system of equations, you try to use the least squares minimization principle, which essentially boils down to minimizing the error functional defined by summation Wj, phi j estimated minus phi j the whole square. This is minimized with respect to the gradients, and that ends up with getting a local system of equations for every cell that one needs to solve for. Typically, the weights are inverse distant weights, and you are essentially trying to give more priority to the closer neighbors than the farther neighbors. The green-gauze reconstruction, on the other hand, doesn't require any matrix inversions to find out the gradients. Rather, it utilizes the divergence theorem. Here, you get a closed form expression for the gradients, but the idea is that you need to take care in defining the phase value that appears in this expression. If the phase values are not second order accurate, you do not get consistent gradients, and therefore a lack of consistency could reflect in the lack of accuracy of these gradients. You could go with a simple averaging, but this leads to inconsistent gradients, which is well known, and this can also affect the solution accuracy, as we shall see in a while. So if you have these gradient schemes, why is it that we need to look at a unified view for gradient schemes? Turns out that even though these are popular gradient schemes, they come with issues. For instance, LSQ gradients with phase sharing neighbors are known to be unstable on triangular and tetrahedral meshes. Green-gauze gradients are clearly inconsistent on irregular meshes unless you take care to ensure that the phase values are second order accurate. Least square gradients, while they are quite popular and first order accurate on irregular meshes, lose out on the accuracy on curved and stretched grids, where interestingly, the GG gradients show good accuracy. And if you have inaccurate gradients, you can have a stable Euler solver, but you have unstable viscous solvers. So clearly you have two aspects here. One is the accuracy of the gradient, which is important for the accuracy of the solution, but you would get a solution only if you have a robust flow solver, which is again affected by the gradient scheme. So there are possible solutions people have suggested, and it is in this direction, which involves devising accurate and robust gradient schemes, that we try to come with a fresh perspective to look at gradient schemes on unstructured meshes. Our first step in this direction is actually a simple tensor identity, which is very well known. And you can see that for any three vectors A, B, and U, you have this tensor identity that tells that the dyadic product AB transpose actually maps any vector U into another vector which is now parallel to A. So our idea here is that if you can define a suitable neighborhood Okay, so you can see that the neighborhood could be anything, as we shall see shortly. But if you define a suitable neighborhood, which could be consisting of faces or face sharing neighbors or a neighborhood of cells around the cell of interest, as long as you can define a suitable neighborhood and define geometric vectors A and B associated with that neighborhood, one could actually go ahead and define a second order tensor, which is essentially a dyadic sum, which reads summation over the faces, the tensor product of AF and BF. Now, if you define this dyadic sum, you can see that you have a dyadic sum vector product identity here. And interestingly, if you're letting U to be gradient of phi and assuming that the dyadic sum is an invertible matrix, you end up getting a very nice looking expression for the cell centroidal gradient. And if you see, this expression for the cell centroidal gradient is actually a vector interpolation strategy. It means that if you have this scalar b dot grad phi at the faces available, you can reconstruct the gradients at the cell provided p inverse is available or excess. So the accuracy here of this particular expression depends upon the choice of A and B, the choice of the neighborhood F, and of course the choice of interpolation, which clearly is not obvious at this stage but would become clearer as we discuss the various schemes. Of course, the dyadic sum, as you can see here, depends on A and B, and we assume that it is invertible, and several possible choices of geometric vectors can lead you to different schemes. And we start with the two schemes that we have already discussed. And these are the linear least squares and the Green-Gauss approaches. So if you can look at the linear least squares approach, you see that if you start by defining A and B as the vector xj minus xi, where j refers to the cell centroid of the neighbor, which is in the vicinity of I, which could both be primary neighbors and secondary neighbors, you end up getting a symmetric dyadic sum. And the identity that we just saw here, b dot grad phi, also can be simplified. And what you end up getting is the same expression that you obtain from a least squares minimization. But here you see that there is no apparent minimization obvious, but yet the formula is still the same. The next step is to try retrieve the Green-Gauss scheme. And if you choose an implicit neighborhood consisting of faces of a cell, where the vector A is now the area vector SF, and the vector B involves xf minus xi, where xf is the position vector of the face center. What you see here is that the dyadic sum actually simplifies to a diagonal matrix involving the volumes, so it's easily invertible, and the result is that you get the same closed form expression that you otherwise obtain by using the divergence theorem. So interestingly, we are able to get the least squares and Green-Gauss scheme by suitably choosing A and B, and we can go one step further and look at what is called as a directional least squares approach, wherein we have chosen A and B as the surface area vector and the unit normal vector to the face. So you are having a compact neighborhood consisting of the faces of the cell, just like Green-Gauss, yet we call this as a least squares approach. Why do we do so? Well, if you see very carefully, you can see that the dyadic sum is still a symmetric matrix, and you have an identity that reduces to a local system of equations that you need to solve for the gradients. Interestingly, you can show that this is actually equivalent to minimizing a functional G defined as follows, where the face areas now can be treated as playing the role of weights. This approach is not new. It's actually been used in literature, but not in the context of finding gradients, but in slightly different contexts, but sparingly in literature. A fourth approach is called as modified Green-Gauss reconstruction, and you can arrive at it simply from the Green-Gauss scheme by switching the A and B vectors. If you switch the A and B vectors, you see that the dyadic sum still remains proportional to the identity matrix, and what you end up with is essentially an identity that now involves the normal derivative at the faces. So if you see here, we have four different families of schemes, or four different schemes, and you can see that the modified Green-Gauss and the directional least squares approach both require the normal derivatives, and they use the same compact neighborhood. But one is a least squares approach because it's equivalent to minimizing a functional, and the other is a Green-Gauss approach because this could have been derived from the divergence theorem as well, as was shown in Deka et al., where the scheme was first proposed. So what did we arrive at? Well, what we have done is that we have a tensor vector product identity that allows us to devise new schemes by a smart choice of geometric vectors. We see that the least square schemes are characterized by parallel geometric vectors. So you can see the least square schemes are parallel geometric vectors. They have they have a symmetric dyadic sum, and you have to solve a local system of equations to obtain the gradients. On the other hand, the Green-Gauss family of schemes have non-parallel geometric vectors, a diagonal dyadic sum, and closed form expressions. And it's very clear that even though the MGG and the DLS belong to least squares and Green-Gauss families, there are certain similarities in terms of the compact neighborhood and the need to find out the normal derivatives. So maybe you can ask, are the Green-Gauss and the least squares families related? Turns out that they are. And we see this by looking at a least squares gradient scheme that we derive by using a compact neighborhood. So if you choose AF and BF, as you can see over here, which are parallel vectors, you see that the identity reduces to a tensor vector product or a matrix vector product, an equation involving a matrix vector product, wherein you can see that the dyadic sum is apparently symmetric like the traditional least squares, but the right hand side involves the phase values like your Green-Gauss approach. And you can then show that if you go here and look at the projection of I onto the line joining the projection of I on the line parallel to the normal vector passing through the phase center, you can see that this is I prime, and xf minus xi prime is essentially parallel to the unit normal vector. So if you use this idea and split the identity, you will be able to show that the method now reduces to something very similar, very obvious and very familiar, and this is nothing but the Green-Gauss gradient scheme, except that there are certain additional terms which essentially are proportional to grid non-orthogonality. So what you end up here is that by a specific choice of weights, of course, as I said here, there are weights which you choose that are proportional to the phase area, and if you choose these weights, it's possible for us to move from this least squares approach to the Green-Gauss approach. And therefore, one can see that the Green-Gauss family can be derived from a least squares approach with a compact neighborhood. So we saw these different families, and we have looked at the MGG and DLS schemes as well. So why is it that we need to look at so much different gradient schemes when you already have traditional least squares and Green-Gauss schemes? Well, we have already said that there are issues associated with these schemes, and if you are proposing new schemes like MGG and DLS, well, clearly they must have some advantages to offer. So do they offer any advantages? Well, that needs to be investigated, and the first step in investigating them is to look at how to implement MGG and DLS. So we start with the MGG scheme, and you can see that the expression for the MGG scheme involves a normal derivative, and the normal derivative can be computed in three possible different ways. The one is the Fursiger and Perick approach, the second is the Schwartz approach, and the third possibility, which is relatively new, involves what is known as an alpha damping approach. You can see that the normal derivative here is split as a consistent part and a damping part involving an alpha parameter. What is common, however, between all the three approaches is the fact that all of these involve not only the gradient at I, but also the gradient at j, which means that if you take these definitions and plug it back into the expression, you end up getting a implicit scheme, and therefore you need to essentially use an iterative approach to obtain the gradients. That's really a costly affair, particularly if you're using it as part of a finite volume solver. But if you have a steady state finite volume solver, one can actually go ahead with a non-iterative approach as well. The interesting part here is to see the role that alpha would play, and if you do a little bit of analysis on uniform Cartesian meshes, you can show that the alpha parameter is essentially a damping coefficient. With smaller alpha, you can see that the gradients get damped, and with higher alpha, you are essentially having much better resolution because of less damping. And the value of alpha equal to 3 is a bit special, as you can see. We have done studies on Cartesian meshes, and you can see that the gradients obtained using this MGG alpha scheme are consistent because the errors decay as the grid gets refined. As the alpha value increases, you can see that the error decreases. The highest errors are for the lowest alpha, indicating that the damping is strong. And on Cartesian meshes at alpha equal to 3, you actually end up getting fourth order accuracy, whereas for all other values of alpha, the scheme simply reduces to the second order central difference scheme. What happens at alpha equal to 3? Well, this is an implicit scheme. At alpha equal to 3, the scheme simply reduces to the central compact scheme of the highest possible order of accuracy, which in this case is 4. Of course, we have tried this on unstructured meshes as well, wherein clearly all alphas seem to perform similarly, though no real advantage, and you essentially get the gradients reducing at a rate of unity, meaning that you have at least first order accurate gradients. Another interesting aspect is to see how the scheme performs for a discontinuous function typical of shocks and contacts. Here again, you can see that as the alpha value is smaller, you have damping and you don't see the peak in the Dirac delta function. However, as alpha is increased, you are able to capture the peak more correctly. However, you have now a loss in monotonicity and oscillations are produced. We have tried using the scheme for the Poisson equation, and you can see that when you try to solve a simple Poisson equation on a unit domain, the larger values of alpha essentially have lower errors, and it appears that a value of alpha equal to 0.5 could be optimal. You have the solution error decaying at the rate of order h square, where the gradients are first order accurate. Clearly, there's no point in talking about these schemes if you don't apply to genuine Euler and Navier-Stokes solvers. And we have done some studies with Euler computations, and you can see here that for the smaller values of alpha, you get faster convergence, indicating the fact that you have a more robust and stable solution procedure. But it's the higher values of alpha, close to 1, wherein you can see that the drag coefficients are minimal. Of course, the drag coefficient for the problem has to be identically 0 because it's an Euler problem. So the closeness of your CD value to 0 is an indicator of how less the numerical diffusion is and how accurate the scheme would be. This is another interesting test case where we tried solving the transonic flow past and NACA 0012 aerofoil. You can see here that for a value of alpha equal to 0.1 and alpha equal to 0.5, no limiters were required. So we were able to capture the shocks without limiting, which typically is needed in a compressible flow solver. However, at alpha equal to 1, you can clearly see that the limiter had to be utilized for stability, which is why you can see that the results for alpha equal to 1 agree with those of alpha equal to 0.1 over here. That said, the MGG is a very interesting scheme, but then it has to have an iterative approach, particularly at every time step. If you're looking at an unsteady scheme, that obviously leads us to a question: is it possible to create a consistent Green-Gauss scheme that is free of iterations? It is, and there are some studies like those of Akkuri and Ishwaran who have proposed an auxiliary volume approach and a nodal interpolation-based Green-Gauss of Holmes and kernel. But these approaches also have issues, and we are trying to see if we can have a simpler approach which is free of these dual volumes and interpolations. Turns out that such an approach exists in literature, and from our unified framework it follows by this choice of AF and BF. This is again a compact neighborhood because we use only primary phase-sharing neighbors, and because A and B are non-parallel vectors, this has to be a Green-Gauss scheme. I'll skip the details for the paucity of time, but it is possible to indeed show that this is actually a Green-Gauss scheme, even though you can see that the matrix or the dyadic sum that you can see over here, or the matrix is not a diagonal matrix. This is indeed a Green-Gauss scheme. The fact that it does not have a diagonal matrix is essentially because it is a consistent scheme by construction, and you can actually derive the scheme as a consistent Green-Gauss scheme, which is also what the unified approach gives. Of course, it's not sufficient to just talk about it as a consistent Green-Gauss scheme. You have to illustrate it, and you can see that we have done studies for a Poisson equation on triangular meshes, where we are able to show that the X gradient errors are decaying at a rate of unity, and the solutions are all second order accurate. And on unstructured grids as well, we get at least first order accuracy on any arbitrary mesh, and it reduces to the second order central differences on a Cartesian mesh. Of course, the explicit consistent approach which is based on the quasi-green technique, is also quite advantageous, particularly when you are looking at thin and curved meshes, where it seems to be better than the green gauze and the unweighted least squares, both of which are inconsistent. The quasi-green Taylor-Gauss gradients are consistent both on structured and triangulated meshes for rapidly varying functions on high aspect ratio meshes, and sometimes actually also are superior to the weighted least square scheme for certain cases. Again, on Euler simulations for a low subsonic flow pass in NACA 00 aerofoil, 0012 aerofoil on both a structured and unstructured mesh, we can see that the quasi-green Taylor-Gauss gradient scheme actually has the lowest CD. On the structured mesh, you can see that it's the green Gauss scheme, which probably has a slightly marginally smaller CD than the QG scheme, and which also explains why on such structured high aspect ratio meshes, green Gauss is favored in the CFD community. However, on the unstructured mesh, the Taylor-Gauss gradient clearly seems to have a superior advantage because its CD value is one order lower than all other schemes. And what is more important to note is that the least square schemes on such meshes actually required limiters for a stable solution, despite the fact that this was a low subsonic flow. So I would like to conclude now by saying that our efforts have led to a simple tensor identity that can encompass well-known and less-known gradient schemes on unstructured meshes. We now have a fresh perspective that allows us for a non-intuitive interpretation of gradient schemes. You can choose A and B vectors with the neighborhood suitably to construct new schemes, and this allows also a natural means to devise hybrid schemes. We have also seen that the green Gauss reconstruction can be recovered from least squares by suitable choice of weights and neighborhood, although the robustness and stability of these schemes for finite volume computations, of course, needs to be evaluated through extensive numerical studies, some of which have been presented as part of this talk. To conclude, we now conjecture that the traditional picture involved gradient schemes classified as least squares and green Gauss, but we do believe now that there is a much larger family of gradient schemes, and the least squares and the green Gauss are only subfamilies, with the green Gauss actually being a subset of the least squares family with a compact neighborhood and cell-dependent weights. So I would like to acknowledge Mr. Mandeep Deka, who did the MGG reconstruction as part of his master's thesis when he was at IIT Guwahati, which actually started off this entire work. We carried out studies with MGG reconstruction with Professor Dalal and his group at IITG, and the unification of the gradient schemes is largely due to Dr. Ashwini, who is currently a DST Inspire faculty at IIT Patna and was previously a postdoctoral associate at IIT Palakkad, and the comments and insights from Dr. Alexandros Sirakos from University of Cyprus with relation to the gradient schemes have also highly benefited our work. So thank you all for your kind attention.
Thank you, Professor Natarajan, for this very interesting talk. We understand that gradient reconstructions are kind of stems of any unstructured finite volume solver, and going into such mathematical detail and actually finding out an interesting truth on that least square method and green Gauss, they are kind of similar approach is very interesting. And mathematically, they're kind of similar. This is very interesting. So I'll request audience, if you have any question, please ask to Professor Natarajan. Any question from audience? And before we get any question from audience, Ganesh, I have a short question.
Yes, Somnath.
Yes. In case you have a skewed mesh, right, how are these schemes performing? It's a very skewed mesh. Say, okay. I would almost say two meshes are making something like more than 180-degree angle, two edges. So in that case, how does this solutions perform?
Okay, so if it's just to calculate the gradient given a function, a skewed mesh, well, clearly the green Gauss scheme is going to be highly inaccurate and inconsistent. The quasi-green Taylor-Gauss gradients would perform quite accurately, but it would be the MGG or the DLS schemes, provided you are able to use enough damping.
Right, that is the question. Like, so damping can help you there.
Yes, significantly help you there. So that's one of the advantages of the free parameter alpha, that you can tune them so that you can introduce stability, but the choice can allow you to have a trade-off between robustness, stability, as well as accuracy. So if you are able to do it through your experiments, depending upon the grid and the function, that allows you that freedom to obtain possibly the best results that you could have.
Okay. Well, one more question from my side. Is that you're telling that this reconstruction scheme is iterative for unsteady flows, but
yes.
how is the iteration costs? I mean, can you start with the last time steps values of the parameters and iterate it over?
Yeah, so essentially the iterative cost could be quite huge. One could go with a fixed number of iterations, but then there is no real guarantee that the accuracy of the computed gradients would be good enough. So you could actually do a fixed number of iterations in every time step for an unsteady problem, but if the iterations are not well converged with a fixed number, like if you fix a number like 10 or 15, it's possible that the iterations don't converge well, so that will impact the accuracy, and you would end up getting inaccurate results, but you would have spent up a lot of cost in doing the iterations per time step. Yeah.
Okay, thank you. Any question from the audience? And if not, then we can probably conclude the session. Thank you very much, Ganesh, for this nice interesting talk.
Thank you, Dr. Somnath, and thank you all for your kind attention.
Thank you, Professor Somnath Rai, for chairing the session.
Yeah, thank you.
Thank you, sir. Now, welcome to the final session of the FMFP 2020. Now, this session will be chaired by Professor Arnab Dey from IT Guwahati. Thank you.
Yeah, I have come online. Now we can start the session.
So there is so much background noise.
Okay, I welcome you all for to this session. It is, I think, 9C. Theme is aerodynamics. There are altogether 6 papers to be presented in this session, and we start with paper number 238. The title is Parametric Investigation Towards the Design of a Scramjet Intake Using Low Fidelity Approach. The author, who is presenting? I think Subhayan Brahmachari, is it?
Yes, sir, I'm presenting, yes.
Okay. You may start.
Hello, everyone. I am Subhayan Brahmachari. I am a postdoctoral scholar working in the Department of Aeronautics and Astronautics, Kyushu University in Japan. I'm going to present before you the work that I have done along with Juva Jyoti Chutia, Dr. Ganesh Natarajan, Professor Vinayak Kulkarni, and Professor Niranjan Sahu. The title of the work reads Parametric Investigation Towards the Design of a Scramjet Intake Using Low Fidelity Approach. As can be understood from the title of the presentation, the work is basically aimed at designing scramjet intakes using low fidelity approaches. Scramjet engines are essentially air-breathing engines, which are capable of generating high specific impulse at hypersonic regimes without having the need to carry oxidizers, and at the same time without having any rotating components. The scramjet engines basically works by compressing the incoming hypersonic flow to supersonic speeds, and which is then fed to the combustor. At the combustor, fuel is injected and the air-fuel mixture gets ignited. The ignited mixture is then expanded via the nozzle to produce the required thrust. As can be understood, the performance of the entire scramjet engine depends on the performance of the scramjet intake itself, as it determines the nature of the flow which is fed to the combustor. To be satisfied, the intake is usually subjected to a design problem. Now coming to the design challenges that we have tried to address in the present work, we are aiming at designing intakes which has high compression and minimum flow non-uniformity at the combustor intake. The intake should have high total pressure recovery and low spillage. And at the same time, the intakes should have low sensitivity to off-design conditions. And finally, we would like to have the preliminary design framework to be reasonably accurate, and at the same time, the turnaround time from the initial guess to the final solution should be rather quick. Now coming to the quantities of interest that we evaluate during the process of design of the scramjet intake, they are static pressure ratio, total pressure recovery, spillage, and flow non-uniformity indicated by the term DI or distortion index. In addition, I would like to introduce few additional quantities. ICR or internal contraction ratio, and is defined as the ratio of the cross-sectional area at the cowl to that of the throat. OCR, which is the ratio of the cross-sectional area of that of the inlet to that of the throat. N represents the number of external shocks, and M represents the number of internal shocks. In the schematic towards your right, N is 3, whereas M is 2. In this slide, we describe the methodology that was adopted to build the low fidelity design approach. Specifically, we make use of the framework that was developed by Prakash Raj and Venkatasubba in 2012. As can be noticed, the entire methodology is based on gas dynamic relationships, specifically isentropic and oblique shock theory. Towards your right, we have the flowchart which describes the low fidelity design approach. We start by making a choice for the free stream pressure, Mach number, and density, followed by the number of external and number of internal shocks. One also needs to provide the height and length of the scramjet intake. Since this is an iterative approach, one needs to give a low value for tolerance, epsilon. We start by making a guess for the SPR, that is static pressure ratio guess. And once that is done, we obtain the value for the shock wave angle beta, flow deflection angle theta, post-shock Mach number, pressure, and density, using the equations given on your left. Once these are done, we find out the difference between the post-shock Mach number and the ME value. When the difference becomes less than the tolerance value that we have defined, that is when the conditions for the external shocks are obtained. We repeat the same calculations for the internal shocks. Only the criteria for the Mach number is changed. Once this is done, we finally obtain the conditions at the isolator. Since this is an approach that we have adopted from the open literature, it is necessary to perform a thorough validation study. To that extent, we compare the turning angles that is obtained from the present solver for different Mach number conditions between 5 to 10. And at the same time, different shock are considered. That is 3 external shocks and 1 internal shocks, and 3 external shocks and 2 internal shocks. As can be noticed in the images in front of you, the turning angles compare really well with the data provided by Raj and Venkatasubba for both the conditions. At the same time, it also must be mentioned that the external shocks which emanate from the leading edge of the ramp are constrained to meet the cowl lip to satisfy the shock on lip condition. At the same time, the reflected shock from the cowl are constrained to meet the shoulder ramp, to meet the shock on shoulder condition. These two conditions help us to avoid spillage and at the same time avoid a lot of flow non-uniformity going into the combustor. Since we also estimate the flow spillage and flow non-uniformity using the in-house density-based continuum flow solver for the intakes that are obtained from the present low fidelity approach, it is also necessary to do a validation study for the high fidelity flow solver. To that extent, we adopt a 2D planar intake that was adopted by Way and Alt in 1996 and simulate an inviscid flow over it using calorically perfect gas, since the entire premise of the present work is based on inviscid flows. We use Euler explicit time stepping and AUSM scheme for convective flux discretization. As can be noted from the image on your right, the non-dimensional pressure distribution over the forebody and cowl shows a very good agreement with the numerical data and also does a reasonable job with the experimental data. And finally, we compare the estimates that are obtained from the low fidelity approach and the high fidelity approach in this table, which also shows a very good agreement and augurs well with the observation in the open literature. In this slide, we compare the performance of the scramjet intakes that are designed using the low fidelity approach. We compare the total pressure recovery and static pressure ratio. It can be noted that the total pressure recovery decreases with an increase in free stream Mach number, whereas the opposite trend has been observed for static pressure ratio. The observation can be explained with the equation that is provided in front of you, where they are seen to be inversely proportional. And at the same time, the static pressure ratio that is obtained from the present low fidelity approach for most of the free stream Mach numbers is observed to be less than 50, which is the minimum recommended static pressure ratio by SMART in 2012, suggesting that not enough compression has been performed. Now coming to the off-design performance analysis that was done to assess the off-design characteristics of the intakes that were designed in the present approach, two specific terminologies were introduced: single geometry and variable geometry. Now, single geometry is that geometry which remains same irrespective of the free stream conditions that is used, whereas variable geometry is that geometry which keeps on changing depending on the free stream conditions that been used. For the present investigation, we use an intake having two external shocks and two internal shocks at a free stream Mach number of 8 and use it as a single geometry, as this was also the single geometry that was used by Delhi et al. On the images on your right, we compare the performance that is obtained from the present design approach and its comparison with the data that is obtained using Delhi et al. For the same scramjet intake. It can be noted that the performance that is provided by the variable geometry is much more consistent as far as its variability with respect to free stream Mach number is concerned. This is true for both static pressure ratio and total pressure recovery. However, the performance that is obtained from single geometry shows a large variation with respect to free stream Mach number. That is, the static pressure ratio can go to as high as 60 and it can be as low as 20 for the lower Mach number, which is considered undesirable from the point of view of off-design performance analysis. Now moving on, here we compare this spillage as well as the temperature ratio that is obtained from the present approach, along with its comparison with the data that is obtained by Delhi et al. It can be observed that the variable design approach consistently leads to zero spillage, irrespective of the free stream Mach number that is employed. This is because in the present design approach, shock on lip condition has been enforced. However, this condition is not enforced by Delhi et al. Hence, their design is always accompanied by a certain amount of spillage. Hence, this plot reinforces the relevance of shock on lip condition. At the same time, for the temperature ratio, it can be noted that for the higher Mach numbers, temperature ratio can be greater than 3, signifying that the post-shock temperature at the isolator can be greater than 850 degree Kelvin, which is desirable from the point of view of spontaneous ignition of the hydrogen fuel. Yet another parameter which is quite important from the point of view of off-design performance is the angle of attack. With this study, we highlight the relevance of shock on shoulder condition as well. Now, on the image on your left, we plot the distortion index on the isolator surface. That is, we adopt a scramjet having two external shocks and two internal shocks at a free stream Mach number of 8. And for various angle of attack, we plot the distortion index. It can be noted that the distortion index corresponding to 0 of angle of attack is the least, signifying that the present design approach is able to generate least distortion index or least flow non-uniformity when it is operated at 0 angle of attack. However, when there is a change of angle of attack, for instance, when the angle of attack is negative, as is shown in the image on your right, there is going to be some spillage and the incident shock from the cowl now hits slightly upstream of the shoulder ramp, leading to greater non-uniformity. This is also true for positive angle of attack, which causes zero spillage, but at the same time, the incident shock from the cowl now hits slightly upstream of the shoulder and also leads to greater flow non-uniformity. In the present approach, we have tried to further reduce the flow non-uniformity by incorporating what is known as a parallel flow condition into the present design approach, and is given by this equation here. Now, this equation signifies that the summation of the external ramp angles must be equal to the summation of the internal ramp angles, signifying that the flow is constrained to be parallel to the exit of the isolator. With the help of this approach, we are now able to replace the second Mach number criteria as well. On the image on your right, we show the flow non-uniformity in terms of distortion index along the isolator for a configuration having 3 external shocks and 2 internal shocks at a free stream Mach number of 5. it can be seen that the with theta condition, that is parallel flow condition, leads to much reduced flow non-uniformity as compared to without theta condition. Now finally, coming to the conclusions, it was observed that the existing low fidelity approach allows for a much quicker design strategy that is reasonably accurate. The variable geometry showed much more consistent off-design performance as compared to the single geometry condition. The shock on lip condition leads to low spillage, and shock on shoulder condition leads to shock cancellation, which leads to flow non-uniformity being reduced at the isolator. The flow non-uniformity was further reduced by making use of parallel flow condition at the isolator. Now these are some of the literatures that were referred to in this work. That's all for my presentation today. Thank you for your attention.
Now, from the audience, if anyone has any question, the speaker may take some questions. Please, you can ask your questions now. From the audience, if anyone has any question, please go ahead. Seems no one has a question. So thank you, Subayan, for your nice presentation.
Thank you, sir.
Okay, now we move into the next presentation. Volunteer, can you put up the next presentation? Yeah. So the next one is the topic is vertical axis wind turbine simulation. The topic, I think the title is numerical simulation of flow past a three-blade vertical axis wind turbine using the actuator surface method.
Everyone.
Please start the presentation.
Okay. This is the presentation for the project titled Numerical Simulation of Flow Past a Three-Blade Vertical Axis Wind Turbine using Actuator Surface Method. As we all know, there is an increasing demand for wind energy, and the biggest weakness of horizontal axis wind turbines is that it can only optimally cater to unidirectional flows. VAWTs are an excellent alternative that can be used in a wide range of topology and work independent of the direction of the wind flow. They also offer the ease of installation and maintenance due to low motor positions. Further, since doing experimental study is quite impractical, we need to have a better and cheap computational approach, at least to perform an initial analysis on the spatial arrangements of the turbines in the farm. The computational time for simulating one rotation of the single turbine to get a converged result is approximately 18 hours. Scaling to 5 rotations of a turbine and then to a wind farm, the computational cost increment is exponential. Thus, a better computational approach needs to be applied to give us a good trade-off between accuracy and computational cost for getting a near accurate approximation of torque measurements and wake profiles. So, the main aim of our work is to develop a framework that enables us to perform computationally cheap wind farm simulations. For creating the framework for the 3D wind farm simulations, the first step was to validate the idea of using actuator surface method with the 2D implementation. The Reynolds average Navier-Stokes equations for continuity and momentum coupled with realizable K epsilon turbulence model were used for solving the base fluid dynamics. So what is actuator surface method? Actuator surface method was proposed by Shen, and it is a modeling technique where instead of putting the aerofoil in the flow domain, we simulate the effect of aerofoil by artificially including the body force that the aerofoil would have applied on the body volume. This is done by modifying the body force term Vi in the Ray's momentum equations. The source term is calculated using the blade equation momentum theorem. These analytical calculations are done for each time step. The cells are first identified on which the aerofoil are supposed to be present. This is then followed by the analytical calculations for the body force. The velocity is taken from the last iteration and used for calculating the angle of attack. The tabulated data for CL and CD are already present in the code using arrays. Using alpha and CL and CD value, we can calculate CN and CT and FN and FT on the same way. Once we have Fn and Ft, we can calculate the Fx and Fy using the azimuthal positions of the airfoil. This Fx and Fy are then distributed along the points on chord line and then further distributed in cells around the aerofoil for a more realistic application of the body force in the flow domain. The next iteration includes the effects of the current body force applications, and similarly the process goes on. This complete setup of analytical relations are manually hooked on top of the base fluent solver using user-defined functions. After some preliminary validations of our understanding of the user-defined functions, we wrote a user-defined function to simulate the complete 2D vertical axis wind turbine. McLaren's thesis is a published and a well-cited thesis with works on vertical axis wind turbine. The full blade Brand's 2D simulation performed by McLaren has been used for validation in this study. Further, an important aspect of our work, the torque predictions, is primarily dependent on thrust coefficients, which is well studied in the simulation and the experimental studies by McLaren. Here we present a graphical comparison between the simulation results from the McLaren's thesis and our results for thrust coefficient versus azimuthal angle. The orange dots are McLaren's data points, whereas the blue pluses are our simulation results. As can be seen, our results are instantaneous results and are taken after third revolution. It can be observed that the results are in a good match for 0 to 90 degrees and deviate significantly after that. Quantitatively, there is an error of 17% in the calculations of the thrust force and torque predictions in calculation of the turbine per rotation. This is a significant error and an improvement is definitely required. As we saw, there is much difference in the thrust coefficient in the turbine after 90 degree. This can be accounted to the physical phenomena called dynamic stall. Evidently, dynamic stall implementation is a necessary step further in the study. Dynamic stall occurs in the flow around an aerofoil during rapidly changing angle of attack of aerofoil. Dynamic stall is a complex fluid flow problem and cannot be modeled exactly. Thus, semi-empirical and empirical correlations have been used previously for accounting the effect of the dynamic stall. Dynamic stall has an effect on the lift characteristics of the aerofoil, and thus the effect was mainly studied with reference to the helicopters as it had an undesirable impact on the lift characteristics of the wings. Thus, predominantly, the empirical correlations are available for high Mach numbers. Several such correlations such as Boeing-Whittle model, Gaumont model and MIT model have been studied and improved over the years, but the empirical nature of studies limits the generality of application of these correlations. One such study, Boeing-Whittle model, tries to emulate the effect and has only one empirically fitted term, gamma. This may work to our benefit as this formula can be easily corrected and modified for our use cases. A raw implementation of the Boeing-Whittle model of the dynamic stall gives us the results plotted here. As can be seen, the results predicted by the Boeing-Whittle model are clearly overshooting in the peak region and are below the actual results in the rest area. Again, these formulas are for high Mach number, and on clear observation, we can see that the Boeing-Whittle model tries to shift the solution in the right direction, but does it in an amplified manner. Further review on Boeing-Whittle model was done and corrected versions were searched for low Mach numbers. After reviewing several papers on modeling the effect of dynamic stall at low Reynolds number and accounting for the fact that the correlations are empirical in nature, we started working on our theory of modifying the Boeing-Whittle model. Our theory takes the review done in the past decade and builds upon the current theory. Another correction factor for the difference term for low Mach numbers is being proposed, which in this particular case accounts to the value of 0.282. This proposed theory is currently under validation and testing for generality at low Mach numbers. The results provided by the theory, as can be seen here, are encouraging in the case of our current simulations. Thus, concluding from the current progress, we can see that the computational approach we have used can be used for achieving significant reduction in the computational cost and also give near accurate solutions without resolving the boundary layer. Thus, after completely implementing the correct Boeing-Vertal model, we can estimate to get a less than 7% error. Currently, we have a proposed correction which we are studying and reviewing. Thank you.
Please ask questions. The speaker may take some questions from the audience. If anyone has any question, please go ahead and ask the speaker. Anyone has any question from the audience? In that case, we move to the next presentation. Volunteer, please put up the next presentation. Our next presentation is on flow field investigation on BWD, BWB aircraft at different angles of attack. The authors are Ovik Arora, Sudeep Das, and Priyank Kumar. It's from BIT Mesra. Now it can start. It can be started. Please start.
Good day to all. My name is Ovik Arora, and I'll be presenting the flow field investigation on BW aircraft at different angles of attack. So we'll just talk about the contents. So we'll just have a brief introduction, moving on to literature review, which basically helped us to come to the objectives. And then we'll talk briefly about research methodology carried out for obtaining the investigation results. And then we'll have a discussion on the same, concluding with the presentation. So what is the blended wing body aircraft? It's basically a configuration in which we have the fuselage and the wing combined into a single lifting surface. There's no complete like a clear dividing line between the two. Now these configurations tend to offer quite a lot of advantages, such as increased internal volume for the given area, and of course a smooth varying cross-section distribution, which prevents any kind of sharp transition regions such as those found between the wing and the fuselage in a conventional design. There are quite a lot of challenges involved for such configurations as well, which involve particularly in the perspective of flight dynamics, in where there's a very tight coupling between the aerodynamic performance and the trim and the stability of the aircraft. There are other concerns pertaining to the commercial applications, such as the passenger safety, comfort, and cabin preservation. And there are tail lift designs which are being carried out, which require special considerations in regard to the airfoils and, of course, the fly-by-wire system. Now, moving on to literature review, we'll talk the one given by the Quinn et al. First, in which he had carried out the baseline configuration as shown in the figure, and had basically optimized the design in order to obtain better results for the coefficients, lifting and drag coefficients. And of course, this is a similar design which we use for current investigation as well. So these were the airfoils used by the author for the same at different locations. Now moving on, another one which had investigation was carried out by Tatsuya. Basically, he had used a similar model as given by N. Quinn, and this is the one which we'll be comparing as a reference in our airfoil force measurements as a comparison. So here the author had basically compared a high-level device such as the gurney flap and seen the effects of the same on the lift and drag coefficients. So moving on with the next, which is Masashi, he had also carried out investigation of similar design as by Tatsuya and N. Quinn, and had investigated the effects of availability of winglets at the end of the aircraft, and had seen improvements in terms of lift as well as in terms of drag for the same. Now, Sierras and Quinn had also discussed about the sweep of the wing of the blended wing body aircraft, and they had varied the variation, like the sweep from -40, that is the forward sweep, all the way up to 55 degrees, making it the rear sweep. So what they had observed was -40 to 10 degrees angle, like sweep angle. They had not observed much of a variation in terms of lift to drag ratio, and instead from 10 degrees to 55 degrees there was significant variation observed. So they settled at around 38 degree, where they had observed the best results considering the lift-to-drag ratio, the moments, and the structural considerations. Now, moving on, Liebeck is one of the pioneers for the wing body aircraft and had worked specifically on a lot of passenger-based designs in the early days of the century. So here we see him comparing the wing body aircraft model with the conventional tube and wing design, and of course they had developed several prototypes for testing as well. So Jeffrey and Graham had discussed on the vertical stabilizer, and one of the few papers who talk about the control surfaces of the aircraft or the control of the aircraft. So here they had discussed about the vertical stabilizers and those at a certain inclined angle, and two stabilizer configurations were discussed and analyzed. So moving on, we have Merslaw, who had discussed, or with this team, who had basically carried out investigations in of the performance comparison between delta wing UAV and a BWV UAV. They found out that BWV has a superior aerodynamic characterization and performance, but however, the delta wing being slightly easy to manufacture and having a bit more robustness in the structural design was again just taken over and used to investigate further, or used to continue the mission further. Now, Parisa has one of the papers which we observed was for UAV designs. In this, they had gone ahead with a hybrid UAV design with lifting fan embedded into the center of the aircraft. So they had discussed with the different fuselage location in comparison to the wing, and further on carried out the investigation on the same. So based on this, what we observed is that there are limited studies on Reynolds numbers, like low Reynolds number flows on BWP, and nobody had really talked much about the flow physics on how the flow going over the blended wing body affects the lift coefficient observed for the same. What we observed is that Reynolds number, sweep angles of the wing, and the angle of attack with the airfoil configuration are the major factors influencing the flow over the blended wing body aircraft. So we'll be talking mostly with the variation with the angle of attack. Now, BWB for UAV, why we are considering them for low Reynolds number flows is because the kind of advantages and the potential which they offer as a UAV platform. So given the higher internal volume, we can now obtain a much better range and endurance for the, of course, that's with the increased aerodynamic efficiency. And of course, with the higher volume, we have much higher payload capabilities. And of course, since some aircrafts are unmanned, the cabin pressure is not an issue, which was there for a passenger aircraft. And larger lifting surfaces can provide a lot of hybrid design configuration possibility. So there are two figures, X-48, the Boeing prototype, and of course, and the Antarctic exploration vehicle, which we had talked about earlier. So based on the result literature review, we had come up to this objective that we can go ahead and study the BWP flow physics at different angles of attack, and then investigate on how that basically affects, how the flow basically affects the force coefficients obtained. And we carried out experimentation analysis, both qualitative and quantitative, from oil flow and force measurements respectively. And computation was carried out using a commercial ANSYS Fluent software. So we had used the 5-component strain gauge balance for our experimental force measurements, and of course, the optimum mix of carbon soot, oil, and oleic acid for the flow visualization. We had used this hallmark incidence mechanism with the yaw kept at 0 degrees, and of course, the model was observed to have negligible vibration under test condition at all angles of attack. So these are model specifications which we had kept same for where we had kept same Reynolds number for the computation and the experimental models. And this basically slide shows the actual model design with some key dimensions and the location of the regions which will be used to discuss. In fact, if we require to make our discussion rather simplify discussion if you want to discuss about any particular region in the same. Models fabricated using fused filament fabrication and of course using the material PETG, and the one on the right is shown to with the holder basically used to mount inside the wind tunnel. So the computation was carried out using grid size of 2.25 million with an SA model, one equation doubles model, which has been known to useful in several literatures for external low speed flows. And of course, we had gone with the residual of 10 to the power minus 5 with the Reynolds number 5500 as mentioned earlier. So we had carried out grid independence tests at for the computation analysis, and we had settled on a grid value of 2.25 million, given that it was not increasing the accuracy with increased number of elements further. So now moving on to results and discussion, what we see here is that we have got a rather good agreement between our current present computation experimental results along with the one shown by Tatsuya, especially at the low angles of attack. Now what we observed is that at higher angles of attack as we move further, we observe a gentle stall characteristics close to about 40 degrees. So here in the figures, it's a bit more clear as to where the experimental and computation has shown to basically bend over close to 40 degrees angle of attack, which we observe to be a stall angle, and the stall characteristics are quite gentle. For CD versus angle of attack, what we see is that there's not much variation as we move all the way till 5 degrees angle of attack, but after that, 5 or 6 degree angle of attack, but after that there's a sudden rise in the drag, and basically it increases linearly further with the angles of attack. So we will discuss about this when we discuss about the oil flow figures further on how the flow patterns we observe could be possible reason for having such kind of an effect. Now, observing the CL versus CD plots and the L by D ratio with the angle of attack, what we observe is we observe the maximum lift to drag ratio at close to 5 degrees angle of attack. We'll have a certain more discussion of the same when we discuss about the oil flow. Now, moving on to the oil flow, what we observe is that at 5 degrees angle of attack, where the major shift in drag was observed, we observe that in locations 2 and 4 shown over here, there's a small separation bubble forming over the main wing in the inboard and the outboard regions of the same. So this separation bubble is basically not completely separated off the wing. The flow is not completely separated off the wings, and the wings are not operating under stall at the moment. However, anything higher than this is expected to cause the wings to stall and thus result in increase in drag. This is probably the region where the lift is still generated, and of course, because of which we are getting a higher L to L by D ratio at this particular angle of attack. Now, if you observe at high angles of attack, say about 20 degrees, where we still observe the lift to increase further and the aircraft not being stalled, what we observe is that the region 4 shows that the wings are basically operating under stall. There is no effect, no variation in the oil particles observed, and there's no effect of flow observed over the same region. Thus, what we can conclude is that the main center body is the one producing the majority of the lift. The region 2 basically shows the flow patterns which are basically spreading outwards, and region 3 marks the separation locations where the flow would be separating off of the main body. Now, when we compare the results at 5 degree oil flow angles with the ones obtained from the CFD, things become a bit more clear. What we observe is that the flow is moving towards the wing tips as it moves along the main wings, and basically is reflected downwards because of the availability of winglets. So this basically allows the flow to be attached onto the wing at such an angle of attack, and further on it basically separates off from the same. So this is why we observe that kind of behavior in terms of, or that the kind of force coefficient what we observe in the results we discussed earlier. Now, coming down to conclusion, what we observe is that the BWP configuration can generate a good amount of lift at low Reynolds numbers, and of course it exhibits a very high angle of attack due to the contribution of center body on the lift production, which we have observed at 20 degree angle of attack in the oil flow. Now, stall was observed at 40 degree angles of attack, and maximum L by D was observed at 5 degrees. Now, at high angles of attack, what one concern could be raised is that any outboard control surface mount on the wings would lose effectivity because the wings are operating under stall. So this is how we basically conclude this is where I conclude my presentation, and just have a look at the references which we went through. So now we are open for questions.
The speaker can take some questions now. I request from the audience, if anyone has any question, please go ahead. If you have any questions from the audience, please ask the speaker. It appears that there are no questions, so I thank the speaker.
Thank you.
Yes.
Thank you all.
Okay, so we can move into the next presentation. Volunteer? Yeah. So
Respected sir, my name.
Start.
Dear friends, myself Dr. Ashish Jagannath Chaudhary from Guwahati College of Engineering and Technology, Mumbai, presenting the undergraduate students' work on experimental evaluation of vortex tube type jet wind turbine performance. The outline of the presentation consists of introduction, background, objective, experimental setup, result discussion, and conclusion. Going to the depletion of fossil fuels and the continuous rising of energy demand, there is a scope for electricity generation using renewable fuels. If we see the World Energy Outlook report, there is a continuous increase in energy demand. Small reduction in energy consumption observed during the COVID pandemic, but the projection after that will keep on rising, and to fulfill this energy demand, the renewable source of energy is the only solution. If we see the renewable energy production country-wise, the figure A represents China, where the wind energy production continuously rises, and there is no effect of COVID pandemic in the year 2020 for the electricity generation using wind in China. It happens in US also, but in India the graph is quite in negative direction in terms of energy generation using wind. The scenario in Indian scenario, the maximum energy generated using the thermal sources, which are fossil fuels, and remaining portion is through the renewable sources, out of which maximum is the wind energy. Now, wind energy generated by using the wind turbines. Those wind turbines are the three-bladed wind turbines, and the wind velocity which is impinging on this wind turbine will convert into the electricity. But there are lot of efforts are being made in order to improve the efficiency of those turbines. One of such efforts has been put upon here. In this, there are three-bladed horizontal turbines which are unable to capture almost 50% of wind flowing across the turbine. The jet engine operation consists of pressure difference causing suction of air. This principle is being incorporated to increase the air velocity and creating turbulence in the wind turbine. This is the basis for the design of wind jet turbine in order to increase the rotor speed and to capture more wind. There are so many researchers who are working in this area, like Pemu Kas, who is working on the S-type 7S wind turbine. He included additional fins to the turbine blades to increase the electrical power generation. Then Sahil et al. Have worked upon the wind turbine system under different parameter effects. They also have found that the effect of air characteristics on mechanical electrical power are important. Van Bang studied determination of performance parameter on vertical axis wind turbine. Vishal did the jet wind turbine analysis. Peter wind turbine blade design. Roy and Saha did Sylvanus wind turbine, where they reported 40 to 50% of efficiency for the horizontal wind turbine and up to 30% efficiency for the vertical axis wind turbine. Other authors like Kale and Verma were work upon the NSCA 4412 aerofoil blade and 800 mm length of the blade for generating 600 watt power. They were developed. Sarkar and Behra also designed wind turbine of 1 meter diameter for 1 kilowatt power, approximately running at 7 meter per second. Kishore reported first systematic effort to design development of small scale wind turbine. Small scale wind turbine are most efficient wind turbines and working at very low wind speed. Overall efficiency up to 50% were achieved during experimentation by the authors. Wind tunnel experiments revealed has rated power output of 1 kilowatt at 4 meter per second. Since wind energy conversion system is largely dependent on maximizing energy extraction, rotor aerodynamics play important role. Hub and blade of the wind turbine, which are the important components, need to be performance efficient. The literature revealed that study of small scale wind turbine with jet propulsion was missing, and hence need to add. So the working of jet vortex tube type jet wind turbine consists of a turbine blade. They are accommodated in the vortex casing, outside of which is a cowl. There are inside vanes and outer frame. This outer frame is called cowl. Now, lobe mixer. This is lobe mixer. This is lobe mixer. Lobe mixer works. There are two sides for the lobe mixer: stator and the rotor. Stator will guide the air to flow over the blades and efficiently, and cowl functions as to guide the air which is outside this circumference of the blade to move in a forming a proper vortex behind the blade or behind the rotor blade. This vortex formation behind the rotor blade causes the pressure difference, and due to this pressure difference, the air which is being impinging on the blade will be with higher velocity due to suction occurs, and due to the higher velocity, lift force generated on the blade is more, and in turn the electricity generated is more. Experimental setup consists of the wind jet turbine. This is the wind jet turbine which is attached at the end of the wind tunnel. This wind tunnel will be a laboratory setup developed in order to create effect of air with a required velocity. So blower is used for different mass flow rate at atmospheric pressure, and there are different measuring instruments. This is the anemometer for measuring the air velocity. This is tachometer for measuring the rotor speed, and rope brake dynamometer for measuring the torque. The variable frequency drive, ABB make variable frequency drive is used to vary the frequency of a blower. The specifications of the components consist of cowl, shaft, stator, rotor, lobe mixer, wind tunnel, stem. Rotor is of 230 mm diameter. Uncertainty analysis has been carried out for the measuring instruments: anemometer, tachometer, spring balance. The uncertainty found for the output power in terms of percentage uncertainty, that is 1.3%, and efficiency is 1.6%. The results plotted for outlet velocity with the percentage opening. The outlet velocity will keep on decreasing with the increasing percentage opening. This is for the reason of increasing area, so that mass flow rate will be increased, so that velocity will be reduced. So the velocity is 4.3 meter per second to 2.7 meter per second for all the trials. The spring balance deflection with the increase in percentage opening the spring balance, the spring deflection keeps on reducing. This is for the reason of decrease in air velocity. The spring balance record 118.75 gram at 4.3 meter per second, showing 15% decrement at 25% opening. The torque has been calculated at velocity 4.3 meter per second. The torque reported was 0.031 Newton meter, showing decrement of 22%, 38%, 48% for 50, 75, and 100% opening. This is in turn again velocity. If the velocity decreases, then the lift force which is generated gets reduced, and in turn torque will be reduced. The input power which is required to generate the air velocity will be keep on increasing with the increase in the percentage opening. The increment of 32%, 33%, and 29% in input power for the iterations 1, 2, and 3 respectively were recorded. Output power calculated. Output power is 2 pi nt by 60. The output power of 4.27 watt has been obtained at 25% opening. The power found reduced with the increase in mass flow rate of air. The overall decrement of 34% has been recorded. The voltage will be measured using the voltmeter at the generator connected to the rotor shaft, and it is found that at 19.85 volt will be available at 25% opening, and it is showing decrement of 58% whenever reaches up to 100% opening. The efficiency, which is the overall efficiency of the system, this overall efficiency will be 59.15% at 25% opening, which is almost steady up to 50% opening, but thereafter there is a decrement for all the iterations. means there is the efficiency is more or less constant with the slight variation in the velocity, because velocity will no more constant, it keeps on reducing, but the efficiency will be steady during this period. So decrement of 1.3% and 6% respectively at 75% and 100% opening. 50% opening, 59.48%, 59.31% and 58.13% has been achieved for the different trials. Conclusion: with the increase in wind velocity, torque carrying capacity of the turbine found to be increased by 26.22%. This may happen due to the turbulence generated by the vortex shape of turbine casing. The brake power also found increase with the increment in velocity of air by 16%. The overall efficiency, which is an important parameter, is in the range of 50 to 59%. The efficiency increases with the increase in wind velocity, but after a certain limit of wind speed, the efficiency starts to decrease. This vortex shape type of jet wind turbine is found to be more suitable over conventional wind turbine.
If anyone has any question, the speaker may take the question. From audience, please, if you have any doubt, please ask the speaker. If you have any doubt, please ask the speaker any question. It seems nobody has any question for this particular presentation. We thank the speaker and move to the next presentation.
Thank you, sir.
Thank you, sir. The next presentation is on design optimization and off-design performance study of an axisymmetric scramjet intake for ascent flight. It can be started.
Hello everyone, I am Shuvayan Brahmachari. I am a postdoctoral research fellow working in the Space Transportation and System Engineering Laboratory in the Department of Aeronautics and Astronautics, Kyushu University, Japan. I'm going to present before you the work that I myself have done along with Chihiro Fujio and Mehmet Aksai under the supervision of Hideaki Ogawa. The title of the work reads Design Optimization and Off-Design Performance Study of an Axisymmetric Scramjet Intake for Ascent Flight. As can be understood from the title of the presentation, the basic premise of the work is aimed at designing scramjet intakes. Now, before I go into greater technical details about my work, let me give you a brief introduction about scramjet engines. These are air-breathing engines which are capable of generating high specific impulse at hypersonic regime. And it does not need to carry along with it oxidizers like a rocket engine does, and at the same time it does not contain any rotating component like a turbojet engine does. How a scramjet engine works is basically it compresses the incoming air from hypersonic speed to supersonic speeds, which is then fed to the combustor. Now in the combustor, the fuel is injected, the air-fuel mixture gets mixed and then ignited. The ignited mixture is expelled via the nozzle to produce the required thrust. As can be understood, the performance of the entire scramjet engine is largely dependent on the intake itself, because it determines the characteristics of the flow which is fed to the combustor. With so many design criteria that is to be satisfied, the intake is subjected to a multi-objective design optimization problem. Some of the design challenges that we have tried to address in this present study are to have a lower bound on the mean exit temperature of the intake exit from the requirement of spontaneous combustion. Then we tried to minimize intake drag and maximize compression efficiency. And we also studied the off-design sensitivity of the intakes that we have designed. Finally, the computational expense of such an CFD-based optimization framework is reduced with the help of surrogates modeling, which I'm going to explain in the subsequent slides. On the image that you can see in front of you is basically the schematic of a 3-ramp intake that we have tried to optimize. The intake is represented using 6 variables. Hence, we have 6 decision variables, which are basically the 3 ramp increment angles, theta 1, delta theta 2, and delta theta 3, followed by the lengths of the second and the third ramp. And finally, we have the intake exit radius RC. To have a constant intake mass flow, we keep the intake radius Ri constant. Now coming to the objective functions, we try to minimize the intake compression efficiency loss as well as the intake drag, subjected to the constraints that the mean exit temperature at the intake exit has to be greater than 850 Kelvin. The minimum wall shear stress has to be greater than 0, signifying no separation, and the energy residual has to be less than 10 raised to the power minus 4. The objective functions are calculated as given here, and the optimization is performed at 2 design conditions separately, and they are given as follows. There is the first one being at an altitude of 30 kilometers and a Mach number of 7.7. The second one being an altitude of 33.5 kilometers and a Mach number of 10. This trajectory defines the ascent trajectory of this scramjet that we are trying to optimize, and both are at a constant dynamic pressure of 49.7 kilopascal. Optimization is performed using non-dominated sorting genetic algorithm NSGA2 code. Moving on, we use a commercial CFD code ANSYS Fluent as the flow solver. The flow field is assumed to be viscous turbulent. The fluid is calorically perfect, and the viscosity is modeled using Sutherland's law. The computational cost of such a CFD-based optimization framework is reduced by making use of surrogate models, where we replace the actual CFD evaluations from predictions from the surrogate models like response surface models, kriging approximations, and radial basis function. Out of all those models, the one with the least error is chosen to give us the prediction for the objective function and constraints. The error tolerance value is 20% for the objective functions, where it is 25% for the energy residual value. For the present study, we use Gmesh open source mesh generator to create the structured meshes, as can be seen in here. For mesh sensitivity study, we use 3 variants of the meshes: coarse, nominal, and fine, whose cell counts are provided. Now, from the wall pressure distribution along the ramp surface, it can be noticed that it is rather insensitive to the mesh used. So, keeping in mind the balance between computational accuracy and cost, we adopt nominal mesh for the present studies. We have also performed a preliminary validation test case where we compare the numerical data obtained from the present flow solver with that of the experimental and the numerical data obtained from SCRAM Space program operated in University of Queensland. The geometry and the computational domain for that validation test case is shown on your left, and the computational data obtained from the present solver, that is pressure coefficient along the entire length of the geometry, is compared with the experimental and numerical data, and it shows a very good agreement and justifies the choice of the present flow solver. Now, coming to the results and discussion section, here we present before you a set of all the data that are obtained at the end of 28th generation. The images on the left hand side shows the data that are obtained for Mach number 7.7 design condition, where it is seen that the non-dominated solutions, which are the set of optimal solutions, that separates the infeasible solution from the feasible solution. And the non-dominated solutions incur a drag of at least 150 newtons. And this is much lower for the higher Mach number case, that is Mach number 10, which is surprising, but it can be made sense because the phase stream pressure for the Mach number 10 case is much lower, which results in lesser drag. Now coming to the bottom left-hand corner of the screen, which shows the temperature versus drag distribution for all the set of data, here we can notice a positive correlation, which has previously been explained and theoretically justified as well in a previous study by Ogawa and Boyce in 2012. What we can notice from these images is that with an increase in temperature, the slope of the positive correlation between drag and temperature increases, which means with increase in drag, the mean exit temperature is also going to increase at a much higher rate for the higher Mach number. Now, in order to understand the optimal geometries into greater details, few representative geometries from the non-dominated solutions have been chosen, and they are named as F1, F2, and O1. F1 refers to the intake with the highest drag or least compression efficiency loss, F2 refers to the intake which has the lowest drag or highest compression efficiency loss, and O1 is the intake which is a balance point somewhere in between. The decision variable corresponding to each geometry for both the design conditions are shown in the tables right in front of you. It can be noticed that there is sufficient difference in the geometries among themselves, which also serves a good point. In this slide, we show the temperature distribution obtained for the O1 geometry using adaptive mesh refinement for both the design conditions. We use gradients of static temperature to divide a cell into further subcells, which allows for a much crisper resolution of the shock structure. Now, on the image on your left-hand side, you would notice the O1 geometry has a much larger delta theta2 value, which is why we have a shock emanating from the leading edge of the second ram, and it passes through the intake exit, which is not the case for the image on your right hand side because of much smaller delta theta2 value. As a result of this, we have greater flow non-uniformity at the intake exit for Mach number 7.7 case, and is much lesser for Mach number 10 case. In this slide, we try to get a physical intuition behind the drag incurred by each representative geometries. We start by comparing the wall pressure distribution and the wall shear stress distribution for each representative geometries. It can be noticed that the F1 geometry, which is the longest of all, incurs the highest wall pressure as well as the highest wall shear stress, which means that it contributes towards greater screen friction as well as pressure drag, which can be confirmed from the bar plots below. Secondly, it must also be reminded that the compression efficiency can be represented in terms of the mean pressure at the exit and the mean pressure at the inlet, signifying that your compression efficiency is also related to the wall pressure distribution and the mean exit pressure, which means greater the mean exit pressure, greater would be the compression efficiency. Hence, it is noticed that the intakes which are longer, not only do they have greater overall drag, but they also have greater compression efficiency. In this slide, we compare the intake-exit flow profiles, specifically static pressure and static temperature, for the representative geometries for both design conditions. It can be noticed that intakes with smaller exit radius tend to have greater static pressure as well as greater static temperature. In this slide, we compare the off-design performance of the scramjet intakes that have been designed so far. Specifically, if a geometry has been designed at Mach number 7.7, it would then be evaluated at Mach 10 and vice versa. We can see from this table that the O1 geometry, which was feasible for Mach number 7.7 condition, is now infeasible when it is operated at Mach 10 condition with respect to the mean exit temperature condition. This is also true for the other design condition, that is O1 geometry designed at Mach 10 is also infeasible for Mach 7.7. In this slide, we compare the data obtained from the global sensitivity analysis that is performed for both design conditions. Specifically, we study the influence of the 6 decision variables on the 2 objective functions in terms of first order as well as the total sensitivity index, STI. It can be noticed from both the plots that the intake exit radius RC plays a dominant role for both the objective functions. Now coming to the conclusions, what we have observed from the present study is that the non-dominated solutions have been able to outperform the baseline geometry in terms of greater compression efficiency and mean exit temperature, but that comes at a cost of greater drag. The intake exit radius were found to play a crucial influence on both the objective functions at both design conditions. And finally, from the off-design performance analysis, we have observed the intakes that were designed for a particular design conditions were infeasible when operated at a different design condition. Hence, one needs to perform a multi-point design MDO. And finally, these are some of the literature that were referred to in this work. And that's all for my presentation today. Thank you for your attention.
The speaker can take some questions. I request the audience, anyone having any question, please go ahead and ask the speaker. Anyone having any question? Please ask the speaker. Seems no response from the audience, so we can move to the next presentation. Thank you, Subhan, again.
Thank you, sir.
The next presentation is on surface heat flux analysis for opposing jet and combination techniques in the presence of real gas effect. Its presenter will be Ajay Vijay Patil. It's from the Department of Mechanical Engineering, IIT Guwahati. It can be please start.
Hello, I am Ajay Patil from Mechanical Engineering Department, IIT Guwahati. I am going to present my work on surface heat flux analysis for opposing jet and combination techniques in the presence of real gas effects. Content of my presentation are introduction, literature review, objectives of the current study, model description, mathematical formulation, simulation methodology, validation with literature, experimental data, grid independent study, results and discussion, and at last some conclusions. Introduction. High surface heating and large wave drag are common problems during high-speed flights, and these problems should be properly mitigated for efficient and effective flights. Various techniques are available to do so, which include active techniques like counterflowing jet and upstream energy deposition, and passive techniques like cavity and spike. In the current work, combination of jet and cavity is studied. Literature review. Finlay studied the effect of jet pressure ratio on drag force, and he concluded that surface pressure was found to be lower in recirculation region, which was near the stagnation point, and it increased to maximum value where the flow is reattaching to the body. Hayashi and et al. Studied the effect of opposing jet on surface heat flux, and they concluded that for lower jet pressure ratios, the flow field was unsteady, and it gave higher surface heat flux as compared to no jet case. Lu and Liu studied the effect of combination technique on surface tension number, and they concluded that opposing jet gives better cooling performance at lower pressure ratio, and combination technique provides better cooling performance at higher pressure ratio. Min et al. Studied the effect of jet properties on drag force, and they concluded that reduction in wave drag was seen for larger jet Mach number. Objectives of the current study. From literature review, authors concluded that study of real gas effect on counterflow injection technique is limited. Understanding the effect of non-equilibrium nature of the flow on the combination technique. Analysis of drag reduction and surface heat flux for hypersonic flows over hemispherical body. Model description. Figure shows the computational domain with its appropriate boundary condition. In this study, body radius is 25.5 mm and size of domain is 70 mm in x and y direction. Injection radius is 2 mm and ball temperature is kept constant at 300 Kelvin. Flow conditions. Table shows the properties of the free stream and opposing jet. Air is taken as working fluid for both the flows. Pressure ratio is defined as ratio of total pressure of the jet to the total pressure of the free stream flow, and its value is taken as 0.1, 0.2, and 0.4 in the current study. Mathematical formulation. The current slide shows the fundamental governing equations for viscous, laminar, two-dimensional axisymmetric flow over hemispherical body. This continuity equation takes chemical non-equilibrium nature of the flow into consideration. Here the total energy, shear stress components, diffusion velocities, mixture pressure, and surface tension number are calculated by the respective formulas. Simulation methodology. Finite volume method is used to discretize the governing equations. Structure mesh is used throughout the entire domain. Advective upstream splitting method is used to update the conservative flux in each iterations. Venkatakrishnan limiter is adopted for faster conversions. No slip, viscous, and isothermal boundary conditions is used. Convergence criteria is kept fixed at 10⁻⁴. CFL number is kept constant at 0.01, and Gauss-Seidel approach is used to calculate flux at wall and axisymmetric boundaries. Figure shows the validation of current reacting solver with available literature experimental results of Shravanan et al. For no cavity case. From the figure, it is seen that surface Stanton number for current solver matches well with experimental data, and maximum discrepancy is well within 10%. Figure shows grid independent result for no jet and no cavity case for 4 different grid, namely 70,000, 1,40,000, 2,10,000 and 2,80,000. From the figure, it is observed that surface Stanton number for 2,10,000 and 2,80,000 grid size is almost same. Table shows the coefficient of drag for the above mentioned grid size, and the percentage difference in coefficient of drag is less than 0.04% after 2,10,000 grid size, and thus this grid size is taken to carry out all further numerical simulations. Figure depicts the surface Stanton number for no jet cavity case, only opposing jet case, and combination of jet and cavity case for 0.2 and 0.4 pressure ratio. From the figure, it is observed that surface Stanton number reduces sharply with the introduction of jet, and it further reduces slightly with the introduction of cavity. Combination case for 0.4 pressure ratio gives the least Stanton number. Figure shows that the shock standoff distance for no jet and no cavity case is larger than shock standoff distance for cavity and no jet case, and thus the drag forces on the body for no cavity no jet case are much higher as compared to the cavity no jet case. Figure shows mark contour comparison for only opposing jet and combination of jet and cavity case for 0.1 pressure ratio. From the figure, it is seen that flow expands more for combination case, which shifts the reattachment point downstream on the body surface, which gives lower Stanton number for combination case as compared to only opposing jet case. Similar trends are obtained at higher pressure ratios. Table shows the drag values variation for only opposing jet and combination case with jet pressure ratio. It is observed that the drag values rises slightly with jet pressure ratio for only opposing jet case, while it increases very rapidly for the combination case. Figure shows variation of surface Stanton number for various free stream total enthalpies for reacting and perfect solver cases. It is observed that reacting solver gives higher surface Stanton number as compared to perfect solver case for both the free stream total enthalpies, but this difference reduces at higher free stream total enthalpy. Here, reacting solver takes thermal and chemical non-equilibrium effect of the flow into consideration for the calculation of conservative fluxes, while perfect solver calculates the conservative flux with perfect gas assumption. Figure shows the temperature contour comparison for reacting solver and perfect solver cases for 2 megajoule per kg free stream total enthalpy. From the figure, it is seen that shock standoff distance for perfect solver case is larger as compared to reacting solver case, and thus high temperature zone behind the shock stand further away from the body surface for perfect solver case, which is responsible for the lower surface Stanton number for perfect solver case. Major conclusions drawn from the current studies are as follows. The values of the surface heat flux computed from the current reacting solver matches well with the literature experimental data of Shravanan et al. Surface heat flux reduces with the introduction of jet, and it also further reduces with the introduction of cavity as well. Surface heat flux is found to be higher for the reacting solver cases as compared to the perfect solver cases for all the given pressure ratios. Least Stanton number is found for the combination case at higher pressure ratio of 0.4. Introduction of cavity leads to the increment in the drag force on the body surface for all the pressure ratios. These are the references of the current presentation. Thank you. Questions and suggestions, please.
The speaker can take some questions. If anyone from the audience has any question, please go ahead and ask the speaker. Anyone having any question, please ask the speaker. It seems there's no question, so we'll wrap up this session with a thanks to the speaker.
Thank you, sir.
Thank you, Professor Arnab Dey, for chairing the session.
Yeah, thank you. So I'm signing out.
On behalf of FMFP 2020, we all thank you for joining this. Now we will have a valedictory session at 4 p.m. Thank you.
tuyau. Tu es trop grand pour comprendre des choses aussi petites.